Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to rest. Tonight we're setting out on a journey that stretches a little farther than usual. In fact, much farther. Not across a country, not across a planet, not even across a galaxy, but across something so vast that even galaxies start to feel like tiny scattered lights in the distance. Our gentle focus tonight is something called the HCB Great Wall. A structure so immense that calling it large almost feels like an understatement. It's often described as one of the biggest known structures in the entire universe. And yet, like many of the most fascinating things in science, it isn't something you could ever see with your eyes, or even fully imagine all at once. It's more like a pattern, a quiet arrangement of matter stretched across unimaginable distances, discovered not by looking directly, but by noticing where something kept happening again and again. Now, before we wander too far into that idea, let me ask you something simple, something that gently brings us back to your own place in all of this. Where are you listening from right now? Maybe you're tucked into bed, lights low, the room just a little quieter than it was an hour ago. Or perhaps you're sitting somewhere comfortable, letting your mind slow down after a long day. And what time is it for you at this moment? It's always a little amusing, isn't it, that while we're about to talk about structures that stretch across billions of light years, we still ground ourselves in something as small and familiar as the time on a clock. If you find this kind of journey soothing, if you enjoy drifting through ideas that are vast but explained gently, I'd be very grateful if you gave the video a like and maybe subscribed. It helps this calm little corner reach others who might be looking for a quiet place to think, or not think too much at all. Now as we begin, there's no need to rush. The universe certainly isn't in a hurry, and neither are we. So take a slow breath, let your thoughts settle, and imagine, just for a moment, that you could step back far enough to see the universe not as scattered stars, but as something with shape. At first, you might picture space as mostly empty. A few stars here, a few galaxies there, all floating in a vast darkness. That's a very natural way to think about it. After all, when we look up at the night sky, that's exactly what it seems like. Points of light, separated by enormous distances, with nothing much in between. But as scientists began mapping the universe in more detail, especially over the past few decades, something unexpected started to appear. When you zoom out far enough, galaxies don't arrange themselves randomly. They form patterns, filaments, clusters, long strands of matter that stretch across space like threads in a cosmic tapestry. And if you keep zooming out even further, those threads start connecting. They weave together into something often called the cosmic web. It's not a web you could touch, of course, but the name fits surprisingly well. Imagine a vast three-dimensional network where galaxies gather along long filaments, leaving enormous empty spaces in between, like bubbles or voids. It's already quite a comforting image in a way. Not chaotic, not completely random, but structured, quietly organized. Now, within this cosmic web, scientists have identified regions that are especially dense, where galaxies cluster together in large numbers. These are called superclusters, and even they are hard to grasp in size. A single supercluster can contain thousands of galaxies, each one with billions of stars. But every now and then something appears that stretches even beyond that. Something that doesn't quite fit the expectations, and that's where the HCB Great Wall begins to enter the story. It wasn't discovered in the way you might expect. No one pointed a telescope and suddenly saw a giant structure stretching across space like a glowing line. Instead, it revealed itself quietly, through patterns in data, specifically through something called gamma-ray bursts. Now, gamma-ray bursts are among the most energetic events in the universe. They're brief, intense flashes of gamma radiation, often caused by massive stars collapsing or by neutron stars colliding. They don't last long, sometimes just a few seconds, but in that short time, they can release more energy than our sun will produce in its entire lifetime. Because they're so bright, gamma-ray bursts can be detected from extremely far away. They act a bit like cosmic lighthouses, flashing from distant corners of the universe, giving us clues about what's happening there. And over time, astronomers started noticing something interesting. These bursts weren't evenly distributed. In one particular region of the sky, there seemed to be more of them than expected. Not just a few more, but enough to suggest a pattern. At first, it might not seem like much. After all, patterns can happen by chance. If you flip a coin enough times, you might get a long streak of heads, but the more data they gathered, the more persistent this pattern became. And slowly, carefully, scientists began to consider the possibility that this wasn't just random. That perhaps these gamma-ray bursts were tracing out something real, something enormous. What they were seeing appeared to be a structure stretching across billions of light years, a region of space where matter was more densely arranged than average, forming something like a vast wall, though not a solid one. More like a loose alignment, a region where galaxies and events were clustered along an extended shape. They named it the Hercules Corona Borealis Great Wall, often shortened to the HCB Great Wall, after the constellations in the direction where it was observed. And just saying its size out loud feels a little surreal. It's estimated to span about 10 billion light years. To put that into perspective, the observable universe itself is about 93 billion light years across. So this single structure, if confirmed as it appears, would stretch across more than a tenth of the entire observable cosmos, which raises a rather gentle but intriguing question. Should something that large even exist? Because according to one of the guiding ideas in cosmology, known as the cosmological principle, the universe on very large scales should be roughly uniform. Not perfectly smooth, of course, but without structures that dominate everything else. In other words, if you zoom out far enough, things should start to look similar in all directions. No giant walls, no preferred regions, just a kind of statistical balance. And yet, here we are, looking at something that seems to stretch that idea. Not necessarily break it completely, but certainly nudge it, as if the universe is quietly saying, well, mostly uniform, but not entirely. Of course, science is careful. Discoveries like this aren't accepted instantly or without question. There's always the possibility that what we're seeing is a statistical fluke, or a result of how we're observing the universe, rather than a true structure. But even the possibility of something this large is enough to make us pause, because it changes the way we imagine the universe. Instead of a smooth, evenly spread out collection of galaxies, we start to see something more textured, more varied, a place where even on the larger scales patterns can emerge that surprise us. And perhaps what makes this idea especially calming, in its own quiet way, is that it reminds us how much there still is to discover. We've come a long way in understanding the cosmos. We can measure distances across billions of light years. We can detect bursts of energy from the edge of the observable universe. We can map the distribution of galaxies and begin to see the outlines of structures that were completely invisible just a few decades ago. And still, something like the HCB Great Wall can appear, almost unexpectedly, like a faint shape emerging from the fog. It doesn't shout for attention. It doesn't demand to be understood all at once. It just sits there quietly enormous, waiting for us to notice. And as you let that idea settle in, you might start to feel a shift in scale. The things that felt large during your day, the tasks, the worries, the little moments of stress, begin to shrink just a bit. Not because they aren't important, but because the universe is so vast that it gently puts everything into perspective. Somewhere out there, across distances so large that even light takes billions of years to travel them, there may be a structure stretching like a faint outline across space, traced not by what we can see directly, but by the events that flicker within it. And here you are, in your own small, comfortable corner of the universe, listening, breathing, letting your mind drift. If you pause for a moment and think about the word largest, it probably feels straightforward at first. After all, we use it all the time. The largest building in a city, the largest animal in the ocean, the largest mountain on Earth. These are things we can compare, measure and picture without too much effort. There's always something to stand next to, something to scale against. But once we step into the universe, that simple idea begins to loosen a little. Because what does largest really mean when there's no edge to stand on, no clear boundary to trace with your finger, no way to step back far enough to see the whole thing at once? Even the act of measuring becomes a quiet challenge. On Earth, if you wanted to measure something large, you could walk around it or fly over it or use satellites to map it. You have reference points. You have a sense of distance that's tied to your own experience. A kilometre, a mile, a horizon you can actually see. In space, those familiar anchors begin to fade. Distances are no longer measured in steps or roads, but in light years, the distance light travels in a single year, moving at about 300,000 kilometers per second. And even that unit, which already feels enormous, becomes just a starting point. Because when we talk about structures like the HCB Great Wall, we're not dealing with a few light years, or even a few million. We're talking about billions. And at that scale, largest stops being a clear label and becomes more of a gentle approximation. Another thing that quietly complicates the idea is that most structures in the universe aren't solid in the way we're used to. When we say wall, it's easy to imagine something continuous, like a long barrier stretching from one end to another. But cosmic structures are not like that. They're more like patterns, clusters of galaxies connected by filaments with vast empty regions in between. If you could somehow travel through one of these structures, you wouldn't feel like you were inside a wall at all. You'd drift through space, occasionally passing galaxies, then long stretches of almost nothing, then more galaxies again. It's a bit like standing in a fog where the droplets are spaced miles apart. The structure is there, but it's not something you could touch or see in one glance. So when scientists say something is the largest structure, they're usually referring to the extent of a pattern, the overall span across which matter appears to be connected or correlated. Not a solid object, but a region where things are arranged in a particular way over a very large distance. And even defining that region requires careful thought, because where does it begin and where does it end? Imagine you're looking at a map of cities connected by roads. At some point, the network becomes so spread out that it's hard to say whether it's still one connected system or several loosely related ones. The boundaries blur, the connections thin out. The same thing happens on cosmic scales. Astronomers look for statistical patterns, regions where galaxies or events like gamma-ray bursts are more densely grouped than expected. If enough of these points line up across a vast distance, it suggests there may be an underlying structure, but it's not always a sharp line. It's more like noticing that a certain part of the sky has a subtle tendency, a slight clustering that, when mapped carefully, reveals something much larger. And that brings us to another quiet detail. We never actually see these structures all at once. Everything we observe in the universe comes to us through light, and light takes time to travel. When we look at something a billion light years away, we're not seeing it as it is now, but as it was a billion years ago. So when astronomers map a structure that spans billions of light years, they're also mapping across billions of years in time. Different parts of that structure are being observed at different stages in their history. It's a little like trying to understand a forest by looking at trees that each exist in a different season. One tree might be in full bloom, another shedding leaves, another just beginning to grow, all part of the same landscape but seen at different moments. So even the idea of a single, unified structure becomes a bit more subtle. It's not just large in space but extended in time. And then there's the question of comparison. When we say something is the largest, we're implicitly comparing it to other things. But in the universe, new observations are constantly being made. New surveys, new data, new ways of looking at the sky. What seems like the largest known structure today might be joined tomorrow by something even bigger, or reinterpreted in a different way. In fact, there are several other enormous structures that have been identified, each stretching across hundreds of millions or even billions of light years. Some are called walls, some filaments, some superclusters. Each one adds a piece to the puzzle, and sometimes they overlap or connect in ways that make it even harder to define where one ends and another begins. So, largest becomes a moving target, a way of describing what we know so far rather than a final, absolute statement. There's also something quietly interesting about the way we as humans respond to these scales. Our brains are very good at handling sizes we can relate to: a room, a building, even a mountain. But once numbers grow beyond a certain point, they begin to blur together. 1,000,000, 1,000,000,000, 10 billion. We understand that each is bigger than the last, but the difference doesn't feel as vivid as the difference between 1 meter and 10. So when we hear that the HCB Great Wall might span around 10 billion light years, it's easy to nod and think, that's very large, without fully grasping just how large that really is. If you tried to travel across it at the speed of light, the fastest speed possible, it would take billions of years, longer than the entire history of life on Earth, and yet, even that comparison only gets us part of the way there. Because space itself is expanding, the distances between galaxies are growing over time, so the structure you're travelling across isn't staying still. It's gently stretching as you move through it. It's a bit like trying to cross a slowly expanding landscape, where the finish line is drifting away from you as you go. All of this makes the idea of largest feel less like a fixed label, and more like a way of pointing towards something that challenges our usual sense of scale. It's not just about size, it's about how we define connection, how we interpret patterns, and how we make sense of something that we can never fully step outside of, to observe in its entirety. And perhaps that's part of what makes it so calming to think about. There's no pressure to fully understand it all at once. No need to hold the entire structure in your mind. It's enough to gently appreciate that such things exist, that the universe contains patterns so vast and subtle that we're still learning how to describe them. You might even notice, as you sit with this idea, that the word largest begins to soften. It's no longer just about being bigger than everything else. It's about reaching the limits of what we can observe, what we can measure, what we can meaningfully compare. And somewhere within those limits, the HCB Great Wall quietly sits, not as a solid boundary, but as a suggestion of structure on the grandest scale we've yet encountered. Imagine just for a second that you could slowly drift away from everything familiar, away from your room, your city, your planet, past the thin blue curve of Earth, beyond the orbit of the Moon, slipping quietly past the planets, the Sun shrinking behind you into just another bright point among many. Keep going. Out past the edges of our solar system, through the sparse cloud of distant icy objects, into the wider galaxy, where stars gather in slow, graceful spirals. Even here, among hundreds of billions of stars, there is still so much space, so much quiet emptiness between them. And then, even further, our entire galaxy, the Milky Way, begins to look small, just one among many. You pass neighbouring galaxies, drifting through clusters where hundreds, sometimes thousands of galaxies gather, each one a vast island of stars, dust, and time. At this point, you might expect the universe to look like a scattered collection of glowing dots spread out evenly in all directions. But something curious begins to appear. The galaxies are not distributed randomly. Instead, they seem to trace out faint, delicate patterns. Long strands where galaxies cluster together, stretching across space like threads. And between those threads, enormous empty regions open up, vast voids where very little matter exists at all. This is what scientists call the cosmic web, and despite the name, it's not something you can see directly with your eyes. It's not glowing or outlined in bright colours. It's revealed slowly, patiently through maps, through careful observations of where galaxies are, and just as importantly where they are not. If you could somehow visualize it all at once, it might remind you of something surprisingly familiar. Perhaps the structure of foam where bubbles press together, leaving thin walls between them, or the branching of roots underground, spreading outward in interconnected paths, or even the delicate network of neurons in the brain, forming connections that carry signals in quiet, continuous flows. The universe, on its larger scales, seems to organize itself in a similar way, not chaotic, not perfectly uniform, but structured, with a kind of gentle order that only becomes visible when you step far enough back. And this idea didn't appear all at once. It emerged gradually as astronomers began mapping the positions of galaxies in greater and greater detail. Early observations hinted that galaxies tended to cluster, but it wasn't until large-scale surveys where millions of galaxies were charted across the sky that the full picture started to come into view. Instead of a smooth distribution, they saw filaments, long, thin structures stretching across hundreds of millions of light years, connecting clusters of galaxies like threads linking beads. Where these filaments intersect, you often find dense regions called nodes, where galaxy clusters gather in large numbers, and surrounding all of this are the voids, immense regions where galaxies are scarce, sometimes spanning tens or even hundreds of millions of light years. It's a bit like looking at a sponge, where the solid parts form a network around empty spaces. But in this case, the solid parts are still mostly empty space themselves, just slightly less empty than the voids around them. And what's especially interesting is how this structure came to be. The cosmic web didn't appear suddenly. It formed slowly over billions of years, shaped by gravity. In the early universe, matter was distributed very evenly, with only tiny fluctuations in density, slight variations, almost imperceptible differences in how matter was spread out. But gravity has a quiet way of amplifying those differences. Regions that were just a little denser than average began to pull in more matter, and as they gathered more mass, their gravitational pull grew stronger, drawing in even more material. Over time, these small fluctuations grew into larger structures. Matter flowed along invisible paths, gradually forming filaments and clusters, leaving behind the vast voids where less matter had been to begin with. It's a slow process, unfolding over billions of years, like a gentle rearranging of the universe's contents. And if you could watch it happen in fast forward, it might look like a kind of cosmic dance. Matter drifting, gathering, stretching, forming patterns that become more pronounced with time. The result is the cosmic web we observe today, a structure so large that it spans the entire observable universe, connecting galaxies across unimaginable distances. Now here's where things become even more interesting in relation to the HCB Great Wall. The Great Wall isn't separate from the cosmic web. It's part of it. In fact, it's one of the most extreme examples of how matter can organize itself within this web-like structure. If the cosmic web is the overall pattern, then the HCB Great Wall is like a particularly long, dense thread within that pattern, a region where galaxies and events seem to align across an enormous stretch of space. But before we focus too closely on that, it's worth lingering a little longer with the web itself, because there's something quietly profound about it. For a long time, humans imagined the universe as either completely chaotic or perfectly ordered, either random, with no pattern at all, or structured in a simple, predictable way. The cosmic web sits somewhere in between. It's not random, but it's not rigid either. It's flexible, evolving, shaped by the interplay of gravity, matter, and time. And perhaps what makes it especially soothing to think about is that it reflects a kind of balance. Dense regions and empty ones, clusters and voids, structure and space. Even the emptiness has a role. Those vast voids, which might seem like nothingness, are actually an essential part of the overall pattern. Without them, the filaments wouldn't stand out. The structure wouldn't have the same shape. It's a reminder that in the universe, as in many things, absence can be just as important as presence. And as you let that idea settle, you might notice how different this is from the way we usually picture space. Instead of thinking of it as a simple backdrop, a stage where galaxies just happen to sit, we begin to see it as something more dynamic, a system where matter flows, gathers, and arranges itself over time. Now, one gentle question naturally follows. If the universe is organised into this vast web, how do we actually know it's there? After all, we can't step outside the universe to take a picture of it. We can't see the whole thing at once. What we do instead is build maps. Astronomers observe galaxies in different directions and at different distances, using powerful telescopes and surveys that scan large portions of the sky. By measuring how far away these galaxies are, they can create three-dimensional maps of their distribution. It's a bit like mapping out a forest by noting where each tree stands, then stepping back to see the overall pattern. And when enough data is gathered, the web begins to emerge. Lines, clusters, voids, all forming a structure that spans across the observable universe. There's also another layer to this. Much of the matter in the universe isn't visible at all. It's something called dark matter, which doesn't emit or reflect light, but still has gravity. And it's this dark matter that plays a crucial role in shaping the cosmic web. In fact, the filaments we see are thought to trace out the underlying distribution of dark matter. Galaxies form along these filaments because that's where the gravitational scaffolding already exists. So in a way, the cosmic web is like an invisible framework, with visible galaxies lighting up its structure, and that adds another quiet layer of wonder. What we see is only part of the picture. There's a deeper structure beneath it, guiding the formation of everything we can observe. As you continue to imagine this, it might start to feel less like a distant abstract concept and more like something gently interconnected. Because every galaxy, including our own, is part of this web. The Milky Way sits within a filament, connected to other galaxies, all of them part of the same vast structure, which means that, in a very real sense, we are part of the cosmic web. Not separate from it, not outside it, but woven into it. And somewhere within this immense network, patterns emerge that stretch the limits of what we expect. Patterns like the HCB Great Wall. Before something as immense as the HCB Great Wall can begin to make sense, it helps to gently build up the picture step by step, starting from scales that are still enormous, but just a little easier to hold in the mind. Because in the universe, size doesn't jump straight from small to unimaginable all at once. It grows gradually, layer by layer, like a quiet stacking of structures, each one resting within something larger. So instead of trying to picture a structure billions of light years across right away, let's begin somewhere more familiar. Not small, exactly, but familiar in a cosmic sense. A single galaxy. If you imagine looking up at the night sky and seeing a faint, misty band of light stretching across it, that soft glow is our home galaxy, the Milky Way. To the naked eye, it looks almost delicate, like a thin cloud. But in reality, it's anything but small. The Milky Way contains hundreds of billions of stars, each one a sun, many with their own planets, their own systems, their own quiet stories unfolding over billions of years. And all of this is spread across a disk about 100,000 light years wide. Even saying that number out loud doesn't quite capture it. If you could travel at the speed of light, the fastest speed possible, it would still take 100,000 years just to cross from one side of our galaxy to the other. And yet, in the larger picture, a galaxy is just the beginning. There are countless others. Some are smaller, containing only a few billion stars. Others are larger, stretching even wider than the Milky Way. Some are spiral-shaped, with elegant arms curling outward. Others are elliptical, more rounded and diffuse, and some are irregular, shaped by past interactions and collisions. Because galaxies don't exist in isolation. They tend to gather. If you could drift far enough away from the Milky Way and look back, you wouldn't see it sitting alone in space. You'd notice nearby companions, smaller galaxies orbiting it, interacting with it, occasionally merging over long periods of time. Together, these form what's known as a galaxy group. Our own is called the local group, and it includes the Milky Way, the Andromeda Galaxy, and dozens of smaller galaxies scattered around them. Even this group is already vast. The distance between the Milky Way and Andromeda alone is about 2.5 million light-years. And yet, in the quiet logic of the universe, they are considered neighbours. Over time, gravity gently pulls them together. In fact, billions of years from now, the Milky Way and Andromeda are expected to merge, forming a new, larger galaxy. Not in a sudden crash, but in a slow, graceful interaction where stars pass by each other across immense distances, reshaping the structure over time. So even at this level, things are dynamic, moving, evolving. Now, if we take another step outward, we begin to see something larger. Galaxy clusters. These are regions where hundreds, sometimes thousands of galaxies gather together, bound by gravity. They are some of the most massive structures held together in the universe. Within a cluster, galaxies move in complex orbits, influenced by the combined gravitational pull of everything around them. There's also vast amounts of hot gas filling the space between galaxies, emitting X-rays, quietly glowing in wavelengths we can't see with our eyes. And once again, there's dark matter. Invisible, but essential. It forms a kind of gravitational backbone, holding the cluster together. Without it, the visible matter alone wouldn't be enough to keep everything bound. Clusters can be enormous. Some span tens of millions of light-years and contain masses equivalent to thousands of galaxies. And yet even these are not the final step, because clusters themselves are not scattered randomly either. They too gather. This brings us to superclusters. A supercluster is exactly what the name suggests, a collection of galaxy clusters and groups linked together across even larger scales. Our own galaxy is part of a supercluster known as Laniakea, a name that means immeasurable heaven in Hawaiian. It stretches across more than 500 million light-years and contains tens of thousands of galaxies. And still, even at this scale, the pattern continues. Superclusters are not isolated islands. They connect along the filaments of the cosmic web, forming extended structures that stretch across the universe. At this point, the idea of building up the scale starts to take on a different feeling. It's no longer just about stacking bigger and bigger objects. It's about seeing how each layer fits into a larger pattern. Galaxies form the basic units. They gather into groups. Groups merge into clusters. Clusters link into superclusters, and superclusters trace out the filaments of the cosmic web. Each level adds another layer of complexity, another step outward, and somewhere along these vast connections, we begin to encounter structures that go beyond even superclusters. Structures that don't fit neatly into a single category. Structures that stretch so far that they begin to blur the boundaries between clusters, superclusters, and filaments. This is where something like the HCB Great Wall starts to make sense. Not as a single solid object, but as an extended alignment of many of these components, galaxies, clusters, and superclusters, all arranged along a region that spans an extraordinary distance. But before we settle too quickly into that idea, it's worth pausing to notice something. At every level we've just explored, from galaxies to superclusters, the same underlying force has been quietly shaping everything. Gravity. It's not dramatic or sudden on these scales. It works slowly, patiently, over billions of years. Tiny variations in density, small differences in how matter was distributed in the early universe, gradually grow under gravity's influence. Regions with slightly more matter attract more material, becoming denser over time, and as they grow, they pull in even more. This process, repeated across the universe, leads to the formation of all these structures. It's a bit like watching droplets of water gather on a surface, small beads forming, merging into larger ones, creating patterns that become more pronounced as time passes. Except here, the droplets are galaxies, and the surface is the fabric of the universe itself. There's also something quietly comforting about the way this hierarchy unfolds. Nothing appears out of nowhere. Everything builds on what came before. Galaxies don't suddenly form at random. They emerge from earlier structures. Clusters grow from the gathering of galaxies. Superclusters form from the linking of clusters. And the larger structures we observe are simply the continuation of that process, extended across even greater distances. So when we talk about something like the HCB Great Wall, it's not an isolated anomaly. It's part of this ongoing pattern. An extreme example perhaps, but still rooted in the same principles that shape everything else. And as you let this layered structure settle in your mind, you might notice how it gently shifts your sense of scale. The Milky Way, which once felt vast, becomes one piece of a larger group. That group becomes part of a cluster. The cluster fits within a supercluster, and the supercluster connects to something even bigger. It's not that anything becomes less important, it's just that everything finds its place within a wider context, and perhaps that's one of the quiet lessons the universe offers. That scale is always relative. What feels enormous from one perspective can become a small part of something larger when you step back far enough. And yet, each layer is still complete in its own way. Your world, your surroundings, your moment right now, all of it exists fully, even within this vast hierarchy. There's no need to hold the entire structure in your mind at once. It's enough to gently trace the path outward, from stars to galaxies, from galaxies to clusters, from clusters to superclusters, and from there into the great interconnected web that stretches across the cosmos. At some point, as we continue stepping outward through these layers of the universe, something subtle begins to shift. Up until now, everything has felt like a natural progression. Galaxies gather into groups, groups into clusters, clusters into superclusters, all following the quiet pull of gravity over immense stretches of time. Each level builds on the last in a way that feels almost expected, like a pattern unfolding exactly as it should. But then, as astronomers kept mapping more of the sky, collecting more data, and connecting more of these distant points, they began to notice something that didn't quite sit as comfortably within that progression. The patterns were getting longer, not just larger in the sense of containing more galaxies, but extended in ways that seemed to stretch beyond the scales they anticipated. Instead of neatly contained clusters, or even loosely connected superclusters, there were hints of alignments that ran across extraordinary distances, almost as if parts of the universe were quietly coordinating themselves along invisible lines. At first, this wasn't immediately obvious. In fact, it's easy to miss something like this when you're looking at the universe piece by piece. Observations often begin as small, localized studies, a patch of sky here, a cluster there, a survey that focuses on a specific region. Each one adds a bit more detail, but it's only when you begin stitching those pieces together that the larger picture starts to emerge, and even then the picture doesn't appear all at once. It reveals itself gradually, like a faint outline that becomes clearer the longer you look. Astronomers began to notice that certain regions of the sky contained more galaxies or more events than expected. Not dramatically more at first, but enough to raise a quiet question. Is this just chance? Or is there something larger connecting these points? Now, this is where things become especially delicate in science, because the human mind is very good at finding patterns even when none exist. We see shapes in clouds, faces in shadows, connections in randomness. It's part of how we make sense of the world, but it also means we have to be careful, especially when dealing with data as vast and complex as the universe. So when these extended patterns began to appear, astronomers didn't immediately declare them as structures. They tested them. They gathered more data, ran statistical analyses, compared observations from different surveys. They asked whether the apparent alignments could simply be the result of random distribution, or whether they were statistically significant enough to suggest something real. And slowly, in some cases, the answer began to lean toward the latter. These weren't just random clusters happening to line up, they seemed to trace out something larger. This is the point where a pattern starts to become structure, not because it suddenly changes its shape, but because our confidence in its existence begins to solidify. We move from noticing something unusual to understanding that it likely reflects an underlying physical reality. It's a bit like looking at a distant mountain range through a light haze. At first you might see only vague shapes, uncertain whether they're hills, clouds, or just a trick of the light. But as the air clears, the outline sharpens, and you begin to recognize the structure for what it is. In the universe, this clearing of the haze comes from better data, better instruments, and more observations over time. And as that happens, the scale of what we're seeing sometimes becomes surprising. Because while the cosmic web already provides a framework for large-scale structure, there are expectations about how far those structures should extend before the universe starts to look more uniform again. This expectation is rooted in the idea we touched on earlier, the cosmological principle. The notion that, on sufficiently large scales, the universe should appear roughly the same in all directions, without any single structure dominating the rest. So when patterns start stretching across hundreds of millions of light years, that still fits comfortably within the framework. Even 1 billion light years, while immense, can be accommodated. But when you begin to see alignments that extend over several billion light years, something starts to feel unexpected. Not necessarily impossible, but surprising enough to prompt a deeper look. And this is where the HCB Great Wall begins to take shape as more than just a collection of points. It emerges as an example of how these patterns, once faint and uncertain, can grow into something that challenges our assumptions about scale. But before we focus too directly on that specific structure, it's worth lingering a little longer with this idea of how patterns become structures, because it reveals something important about how we understand the universe. We don't discover things all at once, we notice hints, then we test those hints, then we refine our understanding, and sometimes, in that process, we uncover something that wasn't part of our original expectations. It's not that the universe is trying to surprise us, it's simply that our models, as useful as they are always incomplete. They describe what we understand so far, but they leave room for new observations to gently expand or adjust that understanding. And when those adjustments happen, they don't usually arrive with dramatic announcements. They come quietly, through data points, through careful analysis, through patterns that slowly become clearer. There's also something quite calming about this process. It's not rushed. It doesn't demand immediate answers. It allows for uncertainty, for gradual refinement, for the possibility that what we're seeing might evolve as we learn more. And that's especially true when dealing with structures on the largest scales imaginable. Because the larger the scale, the more difficult it becomes to define clear boundaries. Where does a structure begin? Where does it end? At what point does a connected region of galaxies stop being one structure and become several? These are not always simple questions. They require careful definitions, agreed upon thresholds, and sometimes a bit of interpretation. So when we say that something like the HCB Great Wall exists, we're not pointing to a solid object with sharp edges. We're describing a region where the distribution of matter shows a coherent pattern across a vast distance, a pattern that is unlikely to be random, a pattern that suggests an underlying structure. And as you let that idea settle in, you might notice how it gently reshapes the way we think about the universe. Instead of seeing it as a collection of isolated objects, we begin to see it as a network of relationships, points connected by patterns, structures emerging from distributions, order arising from what might initially seem like randomness. And perhaps, in a quiet way, that mirrors how we often come to understand things in our own lives. We notice small details, we begin to see connections, and over time, those connections form a larger picture, not all at once, but gradually, gently. So as we continue this journey, the HCB Great Wall will come into focus not as a sudden discovery, but as the result of this process. A pattern that became a structure a structure that now invites us to reconsider just how large the universe's patterns can be. Some discoveries don't arrive with a dramatic moment. There's no single instant where someone looks through a telescope, gasps and says, "There it is." Instead, they begin quietly, almost unnoticed, as small irregularities in data. A few points that don't quite fit. A pattern that seems slightly too consistent to ignore. That's how the story of the HCB Great Wall begins. Not with an image, not with a clear boundary in space, but with a collection of distant signals scattered across the sky, each one brief, intense, and separated by unimaginable distances. These signals are known as gamma-ray bursts. If you think back for a moment, we mentioned them earlier as some of the most energetic events in the universe. They are sudden flashes of gamma radiation, often lasting only seconds, but powerful enough to outshine entire galaxies for that brief moment. They occur when massive stars collapse or when dense objects like neutron stars collide, releasing extraordinary amounts of energy. What makes them especially useful to astronomers is not just their power, but their visibility. Because they are so bright, they can be detected from very far away, across billions of light years. Each one acts like a tiny beacon, a signal that tells us something happened at a specific location in the distant universe. And over time, as more and more of these bursts were recorded, astronomers began building catalogues, lists of where these events occurred, maps of their positions across the sky. At first, the expectation was simple. If the universe is roughly uniform on large scales, then gamma-ray bursts should appear more or less evenly distributed. There might be small fluctuations, of course, but nothing that stands out dramatically over very large distances. But as the data grew, something curious began to appear. Certain regions of the sky seemed to host more of these bursts than expected. Now, this didn't immediately suggest a structure. After all, randomness can produce clusters. If you scatter points across a surface, some areas will naturally have more than others. It's a normal part of statistical variation. So the first response wasn't excitement, it was caution. Astronomers asked a simple question: is this just chance? To answer that, they needed more data, more bursts, more observations, more precise measurements of distance, which is often determined through something called redshift, the stretching of light as the universe expands. By measuring how much the light from these bursts has been shifted, scientists can estimate how far away they are, and therefore when in the universe's history they occurred. This adds an important layer. Because now, instead of just mapping points on the sky, they could map points in 3 dimensions, not just where something is, but how far away it is. And as this 3-dimensional picture became clearer, the pattern didn't fade, it became more pronounced. A particular region, corresponding roughly to the constellations Hercules and Corona Borealis, showed an unusual concentration of gamma-ray bursts at similar distances, not just clustered in the sky, but also grouped in depth, across a range of billions of light years. That combination is what made it intriguing, because it suggested that this wasn't just a random patch of the sky with more bursts. It might be a region of space where matter itself is more densely arranged. A structure. But even at this stage, the idea was approached carefully. Scientists performed statistical tests, asking how likely it would be for such a clustering to occur by chance. They compared the observed distribution to what would be expected if the burst was spread randomly, and the results suggested that the probability of this pattern arising purely by chance was quite low. Not impossible, but unlikely enough to take seriously. So gradually the interpretation began to shift, from a curious clustering to a potential large-scale structure. And because of its apparent extent stretching across an enormous region of space, it was given a name: the Hercules Corona Borealis Great Wall. The name itself carries a quiet sense of scale. Great Wall, not in the sense of a solid barrier, but as an analogy, a way of describing something that extends across a vast distance, connecting points that might otherwise seem unrelated. And yet, even with the name, there was still a sense of caution. Because this wasn't a structure observed in the same way as a galaxy or even a cluster of galaxies, it was inferred, traced through the positions of gamma-ray bursts, which are relatively rare events. Unlike galaxies, which can be mapped in huge numbers, gamma-ray bursts are fewer, and their distribution can be influenced by observational limits. So the question remained, is this truly a structure, or is it a pattern that appears significant given the data we currently have, but might change as more observations are made? This is where the idea of curiosity becomes important. Not curiosity in the casual sense, but in the scientific sense, a willingness to explore something without rushing to a final conclusion. The HCB Great Wall sits in that space. It is a strong candidate for one of the largest structures ever identified, but it is also a reminder that our understanding of the universe is still evolving, and perhaps that's what makes its discovery feel different from something more straightforward. It doesn't present itself as a clearly defined object. It invites interpretation. It asks questions rather than providing immediate answers. There's also something quietly fascinating about the way it was revealed. Not through direct observation of matter itself, but through events, brief flashes of energy that act as markers across space. It's a bit like trying to map a landscape not by seeing the land, but by noticing where lightning strikes. Each strike tells you something about that location, and if enough strikes occur in a pattern, you begin to see the outline of something larger. In this case, the lightning is gamma-ray bursts, and the pattern they trace suggests a region of the universe where these events are more common, possibly because there are more galaxies, more stars, more of the conditions that lead to such bursts. So even though we don't see the structure directly, we see its effects. We see the signals it leaves behind, and from those signals we begin to reconstruct the larger picture. There's a certain calmness in that process. It doesn't rely on a single moment of discovery. It unfolds over time as more pieces of information come together. Each observation adds a little more clarity. Each analysis refines the picture. And slowly, something that was once invisible begins to take shape. As you sit with this idea, you might notice how different it feels from the way we usually imagine discoveries. There's no sudden reveal. No sharp boundary where uncertainty ends and certainty begins. Instead, there's a gradual shift. From not noticing, to wondering, to testing, to cautiously understanding. And the HCB Great Wall, in its quiet way, represents that process. A structure that wasn't seen but inferred. Not built, but discovered through patterns. Not fully understood, but steadily becoming clearer as we continue to look. Long before anything like the HCB Great Wall can be discussed with confidence, there's a quieter challenge that comes first. How do you even see something that large? Not in the sense of looking at it directly, because that isn't really possible, but in the sense of knowing it's there at all. After all, when something stretches across billions of light years, there's no vantage point you can travel to where the whole structure comes into view. There's no edge you can stand on and look back. So instead, astronomers do something a little more patient. They map. Not in the way you might map a country or a coastline, but in a way that slowly builds a picture from countless individual observations. Each one small, each one limited, but together forming something much larger. It begins with points, very distant points. When a telescope observes a galaxy, or a gamma-ray burst, or any luminous object far away, it records its position in the sky. That gives us 2 dimensions, like marking a location on a map using coordinates. But that alone isn't enough, because knowing where something is on the sky doesn't tell you how far away it is. 2 objects might appear close together from our point of view, but one could be much farther away than the other, separated by vast distances along our line of sight. So the 3rd dimension, distance, becomes essential. And measuring distance in the universe is not as simple as using a ruler. Instead, astronomers rely on light. Specifically, they look at how light changes as it travels across space. One of the most important clues comes from something called redshift. As the universe expands, the light from distant objects is stretched, shifting toward the red end of the spectrum. The farther away something is, the more its light has been stretched. By measuring this shift, scientists can estimate how far that object is from us. Not perfectly, but with enough precision to build a meaningful map. And once you have both position and distance, you can begin to place each object in a three-dimensional framework. It's a bit like turning a flat map into a landscape. At first, you only know where things are in relation to each other on a surface. But as you add depth, the structure begins to emerge. Hills, valleys, clusters, gaps. In the case of the universe, those features are galaxies, clusters, and the vast spaces between them. Now, imagine doing this not for a few objects, but for millions. Large sky surveys, carried out over years or even decades, collect data on enormous numbers of galaxies. Each observation adds another point to the map, and as the number of points grows, patterns begin to appear. Filaments, clusters, voids. The cosmic web slowly takes shape. But even with these maps, something like the HCB Great Wall remains difficult to see directly, because it's not a dense, continuous structure. It's a subtle alignment, a region where certain kinds of events like gamma-ray bursts appear more frequently across a vast distance. So instead of mapping galaxies alone, astronomers also map these bursts. Each gamma-ray burst becomes another point in the three-dimensional map, and because they can be detected from such great distances, they extend our reach further into the universe than many other observations. But here's where it becomes especially delicate. Gamma-ray bursts are rare. They don't occur everywhere, and they don't happen all the time. So the map they create is sparse, more like a scattering of beacons than a dense field of points, which means that identifying a pattern among them requires careful analysis. You can't simply look at the map and see a clear shape. Instead, you look for statistical clustering. You ask whether the distribution of these points is consistent with randomness, or whether there are regions where they appear more frequently than expected. And this is where the idea of seeing becomes a little different. It's not about visual clarity, it's about probability. Astronomers use statistical tools to test whether the observed clustering is significant. They compare the real data to simulated distributions, asking how often such a pattern would appear by chance. If the probability is low enough, it suggests that the pattern reflects an underlying structure. Not something we can see directly, but something we can infer. There's a quiet elegance to this process. It's not about forcing the data to reveal something dramatic. It's about listening carefully to what the data suggests, and being willing to accept uncertainty along the way. And even beyond the data itself, there are practical challenges. Observations are limited. Telescopes can only see certain parts of the sky at a time. Some regions are obscured by dust or other sources of interference. Instruments have sensitivities and limits, meaning that some events are easier to detect than others. So the map we build is always incomplete, a work in progress. And yet, despite these limitations, patterns still emerge. That's part of what makes the discovery of something like the HCB Great Wall so intriguing. It appears not because we have a perfect map, but because even within an imperfect one, the pattern is strong enough to stand out. There's also something interesting about how these maps evolve over time. As new observations are added, the picture can change. Patterns can become clearer, or they can fade. A structure that once seemed well defined might turn out to be less significant when more data is included. Or, just as often, it might become even more convincing. So mapping the universe is not a one-time task, it's an ongoing process, a gradual refinement of our understanding, and in that sense the HCB Great Wall is not just a structure, but a moment in that process, a point where the data we have suggests something remarkable, something that stretches our expectations about scale, but also something that remains open to further investigation. As you let that idea settle, you might notice how different this is from the way we usually think about seeing. We often imagine seeing as something immediate. Light enters the eye, and the object is revealed. But on cosmic scales, seeing becomes something slower, more layered. We gather light that has travelled for billions of years. We measure its properties. We place it within a larger framework, and only then do we begin to understand what we're looking at. It's less like opening your eyes and more like assembling a puzzle, one piece at a time, and even then the full picture is never completely finished. There's always another observation to make, another point to add, another pattern to test, which means that what we see is always evolving, and perhaps there's something quietly reassuring in that. The idea that understanding doesn't have to be immediate or complete, that it can grow gradually through patience and careful attention, and that even the largest structures in the universe can be approached in this way, not all at once, but piece by piece. Far out in the universe, there are moments that last only seconds, and yet they outshine almost everything else. Not quietly, not gradually, but in sudden flashes of extraordinary energy, like brief signals sent across billions of light years. These are gamma-ray bursts, and although they are among the shortest events we can observe, they carry an immense amount of information about the distant cosmos. What makes them especially interesting is not just how powerful they are, but how far away they can be seen. Because of their intensity, gamma-ray bursts can be detected from the very edges of the observable universe. Light from these events travels for billions of years before reaching us, carrying with it a snapshot of something that happened long ago, in a place we could never visit. And in a quiet way, that makes them something like markers. Not markers placed deliberately, of course, but natural ones. Each burst tells us, something happened here, and by collecting enough of those signals we begin to trace out where those heres are. To understand why they are so useful, it helps to consider what causes them. There are a few different types of gamma-ray bursts, but many of the most powerful ones come from the deaths of massive stars. When a star, many times larger than our Sun, reaches the end of its life, it can collapse under its own gravity, forming a black hole or a neutron star. In that process, jets of energy are launched outward at nearly the speed of light, producing a burst of gamma radiation that can briefly outshine an entire galaxy. Other bursts are thought to come from collisions between neutron stars, incredibly dense remnants of stars that pack more mass than the Sun into a sphere only a few kilometers wide. When two of these objects spiral into each other and merge, they release a tremendous amount of energy, again producing a gamma-ray burst. In both cases, the event itself is short. Seconds, sometimes even less. But the light continues to travel outward long after the burst has ended, crossing the vast distances of space until, eventually, a small fraction of it reaches Earth. Detecting these bursts requires specialized instruments. Gamma rays do not pass easily through Earth's atmosphere, so most observations are made using satellites orbiting above it. These satellites monitor the sky continuously, waiting for the sudden appearance of a burst. When one is detected, it's recorded almost instantly, and telescopes on Earth and in space can be directed toward that region to gather more information. Over time, this process has built up a growing catalogue of gamma-ray bursts, each one with a position in the sky, each one with an estimated distance, based on how its light has been stretched as it travelled across the expanding universe. And this is where something subtle begins to happen. If you look at just a handful of these bursts, they seem scattered, random, isolated events occurring in distant galaxies. But as the number grows, patterns can begin to emerge. Not obvious at first, not something you would notice immediately, but with careful analysis, certain regions begin to show a higher concentration of bursts than others. Now, it's important to remember that gamma-ray bursts are not evenly distributed simply because the universe itself is not perfectly uniform on smaller scales. Some regions contain more galaxies, more stars, more opportunities for the kinds of events that produce these bursts. So seeing a cluster of gamma-ray bursts in one area is not, by itself, surprising. What becomes interesting is when that clustering extends across very large distances, when bursts that are separated by billions of light years still appear to be part of the same general region. This is what led to the identification of the HCB Great Wall. Astronomers noticed that a number of gamma-ray bursts, all located in roughly the same direction in the sky, also shared similar distances When plotted together in 3 dimensions, they appear to form an extended structure. Not a solid shape, but a region where these events were more common than expected. And because gamma-ray bursts can be detected from such great distances, they allow us to probe regions of the universe that might otherwise be difficult to map in detail. Galaxies themselves can be faint, especially at extreme distances. But a gamma-ray burst, even from very far away, can still be bright enough to detect. So in a sense, these bursts act like beacons, brief flashes that illuminate their surroundings, giving us clues about the distribution of matter in those distant regions. There's something quietly fascinating about that. The idea that events lasting only seconds can help reveal structures that span billions of years and billions of light years. It's a reminder that scale in the universe doesn't always behave the way we expect. Small, fleeting moments can carry information about vast, enduring patterns. And as more bursts are observed, the map becomes more detailed. Each new detection adds another point, another piece of information that helps refine our understanding of how these events are distributed. But this process also comes with challenges. Because gamma-ray bursts are rare, the data is limited. We don't have millions of these events to work with, as we do with galaxies. Instead, we have a smaller sample, which means that statistical analysis becomes especially important. Astronomers must carefully test whether the observed clustering is significant, or whether it could still be explained by chance given the limited number of data points. They also have to consider observational biases. Some regions of the sky are observed more frequently or more thoroughly than others. Some bursts are easier to detect depending on their brightness and distance. All of these factors can influence the apparent distribution. So the interpretation of the data requires caution. Not just excitement at the possibility of a large structure, but careful consideration of how the data was collected and what it truly represents. Even with these challenges, the pattern associated with the HCB Great Wall remains intriguing. It suggests that gamma-ray bursts are not just random flashes scattered across the universe, but can also serve as traces of larger structures. And that idea opens up new possibilities, because if we can use these bursts to map distant regions, we can begin to explore parts of the universe that are otherwise difficult to study. We can look for patterns that might not be visible through other means. We can test our assumptions about how matter is distributed on the larger scales, and perhaps, over time, we can refine our understanding of whether structures like the HCB Great Wall are truly as vast as they appear. As you sit with this idea, there's something quite calming about the way it all comes together. Brief flashes of energy travelling across billions of years, quietly reaching us. Careful observations collected over time, slowly building a map. Patterns emerging not suddenly but gradually. It's not a story of sudden revelation. It's a story of accumulation, of patience, of noticing. And in that sense, the gamma-ray bursts that helped reveal the HCB Great Wall are not just events. They are messages, not sent with intention, but carrying information nonetheless. Messages that, when gathered together, begin to outline something far larger than any single burst could ever suggest. It's one thing to discover something large. It's another thing entirely to discover something that feels larger than it should be. And that quiet sense of should is where the surprise begins. Because when astronomers talk about the size of structures in the universe, they're not just describing what they see. They're also comparing it to what they expect to see, based on the models that have worked very well for a long time. Up until discoveries like the HCB Great Wall, there was a general understanding of how large cosmic structures could reasonably become. Not an exact limit, but a kind of comfortable range. Galaxies gather into clusters, clusters link into superclusters, filaments stretch across hundreds of millions of light years, sometimes reaching toward 1 billion. And beyond that, the universe was expected to begin smoothing out, becoming more uniform when viewed on sufficiently large scales. That expectation comes from a simple but powerful idea. If the universe began in a very even state, with only tiny fluctuations in density, then over time, gravity would amplify those fluctuations, but only to a certain extent. The structures that form would grow, connect, and evolve, but eventually when you zoom out far enough, those differences would average out. Like looking at the surface of the ocean. Up close, you see waves, ripples, patterns moving in different directions. But from far above, the surface begins to look smooth. The details are still there, but they blend together into something more uniform. The universe, it was thought, should behave in a similar way. And for the most part, observation supported that idea. Large-scale surveys of galaxies revealed the cosmic web, with its filaments and voids, but when viewed across very large distances, the distribution appeared to approach a kind of statistical balance. No single structure seemed to dominate everything else. So when the pattern associated with the HCB Great Wall began to emerge, it didn't immediately fit comfortably within that picture. Because its estimated size, around 10 billion light-years, was not just large. It was enormous in a way that stretched those expectations. To put it gently, it raised an eyebrow. Not in a dramatic, this cannot be, sense, but in a quieter, more thoughtful way. Is this consistent with what we know? Or does it suggest that something in our understanding might need to be adjusted? That's the kind of question that makes scientists pause, not because they doubt the data immediately, but because they know how important it is to examine it carefully when something appears to challenge established ideas, and the idea it seemed to touch most directly is known as the cosmological principle. This principle is one of the foundations of modern cosmology. It states that, on large scales, the universe is homogeneous and isotropic. In simpler terms, that means it looks roughly the same everywhere and in every direction. Not exactly the same in every detail, but statistically similar. No preferred locations, no enormous structures that stand out so much that they disrupt that overall balance. And for decades, this principle has worked remarkably well. It underpins our models of how the universe evolves, how galaxies form, how matter is distributed. It helps explain observations of the cosmic microwave background to the faint afterglow of the early universe, which appears almost perfectly uniform with only tiny variations. So when a structure appears that seems to span a significant fraction of the observable universe, it naturally invites a closer look. Because if such structures are common, or if they truly extend to that scale, it might suggest that the universe is less uniform than we thought. Or that the scale at which it becomes uniform is larger than we previously assumed, or perhaps that our interpretation of the data needs refinement. There are several possibilities, and each one carries its own implications. One possibility is that the HCB Great Wall is real, but that it represents an extreme, yet still allowable, fluctuation within the current models. In this view, the universe is still statistically uniform on the larger scales, but rare structures can exist that stretch those limits. Another possibility is that the structure appears larger than it actually is due to the way the data is sampled. Because gamma-ray bursts are relatively rare, the clustering we observe might exaggerate the true extent of the underlying structure. And then there's the possibility that our understanding of large-scale structure formation is incomplete, and that there are processes or conditions that allow for the formation of structures larger than we currently expect. Each of these possibilities is approached carefully, not with urgency, but with patience. Because in science, especially at this scale, answers are rarely immediate. They emerge gradually, as more data is collected, as models are refined, as different lines of evidence are compared. There's also something quietly fascinating about the way this discovery sits between certainty and uncertainty. On one hand, the data suggests a pattern that is unlikely to be random. On the other, the interpretation of that pattern as a single coherent structure remains open to discussion. And that balance is not a weakness, it's part of the process. It allows for flexibility, for the possibility that our understanding can evolve without needing to discard everything that came before. Because it's worth remembering that the cosmological principle itself is not an absolute rule written into the universe. It's a model, a very successful one, but still a model based on observations, and models can be refined. expanded, adjusted to accommodate new data. That doesn't mean they were wrong, only that they were incomplete. As you sit with this idea, there's a certain calmness in it. The universe is not obligated to match our expectations perfectly. It doesn't need to fit neatly within the boundaries of our current understanding. Instead, it offers us clues, observations, patterns that invite us to look a little closer. And when something like the HCB Great Wall appears, it doesn't disrupt everything. It simply adds a new layer to the story. A reminder that even on the larger scales there may still be surprises waiting quietly in the data. And perhaps that's part of what makes this discovery feel so intriguing. Not because it overturns everything we know, but because it gently nudges us to ask deeper questions. About scale, about structure, about how uniform the universe really is. For a long time, one simple idea has quietly guided how we think about the universe. Not because it was proven in every possible way, but because it made sense of everything we were seeing. It gave structure to our models, consistency to our equations, and a kind of calm predictability to something otherwise vast and difficult to grasp. This idea is known as the cosmological principle. At its heart, it's surprisingly gentle. It says that if you look at the universe on very large scales, it should appear roughly the same no matter where you are and no matter which direction you look. Not identical in every detail, of course. There will always be galaxies here, voids there, clusters in one region, and emptier space in another. But if you step back far enough, those differences should begin to average out. The universe should look statistically uniform. It's a bit like looking at a forest. If you stand among the trees, everything feels uneven. Some trees are taller, some shorter. Some areas are dense, others more open. But if you rise high above it, the forest begins to look more uniform, more evenly spread. The cosmological principle suggests that the universe behaves in a similar way. Up close, it's full of variation. Far away, it smooths out. And for a very long time, this idea has worked remarkably well. Observations of galaxies across large regions of space show that on average, their distribution becomes more uniform as you look at larger and larger scales. The cosmic microwave background, the faint glow left over from the early universe, is almost perfectly even in all directions, with only tiny fluctuations. These observations support the idea that, at its largest scales, the universe does not favour one region over another. No special places, no preferred directions, just a kind of quiet balance. This principle is also deeply practical. It allows scientists to simplify their models of the universe. Instead of accounting for every small irregularity, they can assume that on large scales things behave consistently. This makes it possible to describe the expansion of the universe, the formation of structures, and the evolution of matter in a coherent way. In a sense, it gives us a stable foundation, a way to make sense of something that might otherwise feel overwhelming. But like any guiding idea, it comes with limits. Not because it's incorrect, but because it's an approximation. It describes what we expect to see when we look far enough out, but it doesn't forbid the existence of variations within that larger picture. And this is where something like the HCB Great Wall becomes interesting. Because its apparent size seems to push against the scale at which the universe is expected to become uniform. If a structure truly extends across billions of light years, spanning a significant fraction of the observable universe, then it raises a quiet question. At what scale does the universe actually become uniform? Is it smaller than we thought? Larger? Or is the concept itself more flexible than we assumed? Now, it's important to approach this carefully. The cosmological principle is not a strict rule that says, no large structures allowed. It doesn't set a hard boundary beyond which nothing bigger can exist. Instead, it describes a statistical expectation. On average, the universe should look the same when viewed on sufficiently large scales, but on average, leaves room for exceptions. Rare regions where matter is distributed in a way that deviates from that average. So the existence of a large structure does not automatically break the principle. It depends on how common such structures are and how they fit within the overall distribution of matter. If the HCB Great Wall is an isolated case, a rare fluctuation, then it might still be consistent with the cosmological principle. But if many such structures exist, or if they are more common than expected, then it might suggest that the scale of uniformity is larger than we currently believe, or that our models need refinement. There's also another layer to consider. The way we observe the universe is not perfect. We rely on limited data, incomplete maps, and indirect measurements. Gamma-ray bursts, while powerful and far-reaching, are relatively rare events. The patterns we see in their distribution depend on how many we've observed, where we've looked, and how accurately we can measure their distances. So part of the apparent challenge to the cosmological principle might come from the way we're interpreting the data. Not because the data is wrong, but because it is still evolving. As more observations are made, the picture may become clearer. The structure might appear less extensive, or more. The pattern might strengthen, or it might soften. And this uncertainty is not a flaw. It's part of the process. It allows us to explore new possibilities without immediately discarding what we already understand. There's something quietly reassuring about that. The idea that our models are not fragile but adaptable, that they can accommodate new observations, adjust to new data, and continue to guide our understanding even as that understanding grows. The cosmological principle in this sense is not being overturned, it's being tested. And testing is how science moves forward. It's how we refine our ideas, how we learn where they hold and where they need adjustment. And sometimes the most interesting discoveries are the ones that sit right at the edge of what we expect. Not clearly inside the model, not clearly outside it, but gently pressing against its boundaries. As you reflect on this, you might notice how the idea of uniformity itself begins to feel a little more nuanced. The universe doesn't need to be perfectly smooth to be considered uniform. It just needs to be balanced overall. And within that balance, there is room for variation, for patterns, for structures that stand out, not because they dominate everything, but because they offer a glimpse of how complex and layered the universe can be. So when we say that the HCB Great Wall seems to challenge the cosmological principle, it's not a dramatic conflict. It's more like a conversation, a quiet exchange between observation and theory. One suggesting, this is what we see. The other responding, this is how we understand it. And somewhere between those two, our knowledge continues to grow. Not every assumption in science is meant to feel rigid. Some of them are more like quiet agreements, ideas that hold together because they work well, because they explain what we see without too much complication. The notion that the universe is uniform on large scales is one of those agreements. It has guided decades of observation, helped shape models, and provided a kind of steady backdrop for everything from galaxy formation to cosmic expansion. But every so often, something appears that invites a softer kind of questioning. Not a rejection, not a contradiction, but a gentle doubt. And that doubt doesn't arrive as a loud challenge. It comes in quietly, through observations that seem just a little more structured than expected, a little more extended, a little more persistent. The question then becomes less about whether the universe is uniform, and more about how uniform it truly is. Because uniformity in this context doesn't mean perfectly even. It means statistically similar when viewed on a sufficiently large scale, and that phrase, sufficiently large, is where things begin to shift. For a long time, astronomers believed that once you looked beyond a certain distance, on the order of a few 100 million light-years, the distribution of matter would smooth out. Galaxies would still form clusters and filaments, but those patterns would blend into a kind of overall balance. And in many observations, that's exactly what happens. Large galaxy surveys show that while there are dense regions and empty voids, the overall distribution begins to look more even as the scale increases. The cosmic microwave background, that faint echo from the early universe, appears almost perfectly uniform, with only tiny variations. These observations support the idea that the universe, on its largest scales, doesn't favour one region over another. But then there are moments where that smoothness seems to stretch, not disappear, but stretch. Structures like the HCB Great Wall appear to extend across distances that feel uncomfortably large compared to the scale at which uniformity is expected to emerge. And this is where the doubt becomes interesting. Because it doesn't necessarily mean the universe isn't uniform. It might mean that the scale of uniformity is larger than we thought, or that our observations are revealing rare but real deviations within an otherwise balanced system. Or even that the way we define and measure uniformity needs to be refined. There's also something subtle about how we interpret these observations. When we map the universe, we're not seeing everything at once. We're collecting light from different distances, which means different times in the universe's history. A galaxy, 1 billion light-years away, is being observed as it was 1 billion years ago. Another galaxy, closer to us, is seen at a more recent time. So when we build a map of large-scale structure, we're also stitching together a timeline. Different parts of the map represent different stages in the evolution of the universe, and that can influence how patterns appear. A structure that looks continuous across space might actually reflect a sequence of regions that formed at slightly different times, connected by the way we observe them. This doesn't make the structure unreal, but it adds a layer of complexity to how we understand it. Uniformity, in this sense, is not just about space. It's also about time, and that makes the picture more dynamic. The universe is not a static arrangement of matter. It's evolving. Structures grow, merge, stretch, and sometimes fade over billions of years. So when we ask whether the universe is uniform, we're really asking whether this evolving system maintains a kind of balance when viewed across both space and time. And the answer, so far, seems to be yes, but with nuances. There are variations. There are regions that appear more structured than others. There are patterns that extend farther than expected, and these don't necessarily break the idea of uniformity, but they invite us to look at it more carefully. There's also the role of observation itself. Our view of the universe is limited by what we can detect. We rely on light, and light can only travel so far. Beyond a certain distance, we simply cannot see, because the light hasn't had time to reach us yet. This creates a boundary known as the observable universe. Everything we know about large-scale structure comes from within this boundary. So when we talk about uniformity, we're really talking about the part of the universe we can observe. There may be structures beyond that boundary that we will never see. There may be patterns that extend further than we can measure, and that means our understanding is always, in a quiet way, incomplete. But that incompleteness is not a problem. It's part of the process. It reminds us that our models are based on what we can observe and that they can evolve as our observations improve. As you sit with this idea, there's something quite calming about the way it unfolds. The universe doesn't need to be perfectly uniform to be understandable. It just needs to be consistent enough for patterns to emerge, for models to work, for observations to make sense. And within that consistency there is room for variation, for structures that stretch a little further, for patterns that stand out just enough to catch our attention, for discoveries that gently nudge us to ask new questions. The HCB Great Wall is one of those discoveries. Not a contradiction, but a curiosity. A reminder that even on the largest scales the universe may still have subtle features that we are only beginning to notice. And perhaps that's what makes this question so engaging. Not whether the universe is uniform in a strict, absolute sense, but how that uniformity reveals itself, how it balances structure and variation, and how our understanding of it continues to grow. Set beside everything else we've discovered, the HCB Great Wall begins to feel less like a solitary curiosity and more like part of a quiet, growing collection of cosmic giants. Not identical, not neatly categorized, but related in the sense that each one stretches our sense of scale just a little further. Because the HCB Great Wall is not the only structure that has made astronomers pause and look twice. Over the years, several enormous formations have been identified, each revealing something about how matter arranges itself across the universe. And when you begin to compare them, something interesting happens. The idea of largest starts to feel less like a single title and more like a shifting landscape. One of the earlier examples is something called the Sloan Great Wall. Discovered through large galaxy surveys, it extends for about 1.4 billion light-years. At the time of its discovery, it was one of the largest known structures in the universe, a vast collection of galaxy clusters and filaments forming a long continuous region. Even that number, 1.4 billion light-years, is difficult to fully take in. If you imagine light moving at its incredible speed, it would still take 1.4 billion years to travel from one end of that structure to the other. And yet, compared to the HCB Great Wall, it begins to feel almost modest. There's also the CFA2 Great Wall discovered earlier, stretching across roughly 500 million light-years. It was one of the first clear indications that galaxies could form large wall-like structures, hinting at the broader patterns that would later be revealed by more detailed surveys. Then there is the huge, large quasar group, often abbreviated as the huge LQG. This structure is made up of quasars, extremely bright and active galactic cores powered by supermassive black holes. It spans about 4 billion light-years, making it another example of a structure that challenges expectations about scale. And even that is not the end of the list. Another formation, known as the giant GRB ring, was identified using gamma-ray bursts, similar to the HCB Great Wall. It appears as a ring-like arrangement of bursts across a vast region of space, suggesting a large-scale pattern that is still being studied and interpreted. Each of these structures adds another layer to the picture, not because they are identical, but because they show that the universe is capable of organizing matter on scales that are far larger than once imagined. But comparing them is not always straightforward, because, as we've touched on before, these structures are not solid objects with clear edges. They are patterns, regions where matter is more densely arranged, or where certain types of objects, like galaxies or quasars, appear more frequently. And depending on how those patterns are defined, measured and interpreted, the size and shape of a structure can vary. For example, the Sloan Great Wall is identified through the distribution of galaxies in large surveys. The huge LQG is defined by the positions of quasars. The HCB Great Wall is traced using gamma-ray bursts. Each method has its own strengths and limitations. Galaxies are numerous, which provides a dense map, but they can be faint at great distances. Quasars are extremely bright but less common. Gamma-ray bursts are even rarer, but can be seen from very far away. So each structure is, in a sense, revealed through a different lens, and that means that comparing them is not just about size, it's also about how we observe them. There's also the question of connectivity. When we say something is a single structure, we're often describing a region where points appear to be linked in some way. But those links can be loose, extended, and sometimes ambiguous. Two clusters of galaxies might be connected by a filament, but how strong is that connection? At what point does a long chain of clusters become a single structure, rather than a series of loosely related ones? These are not always easy questions to answer, and so, the idea of one structure being definitively larger than another can depend on how those boundaries are defined. Still, even with these uncertainties, a general picture begins to emerge. Structures exist on scales of hundreds of millions of light-years. Some extend to a few billion, and then there are a few like the HCB Great Wall that seem to reach even further. And as you sit with that progression, you might notice something quietly fascinating. The universe does not seem to have a sharp cutoff. There isn't a clear point where structures suddenly stop growing. Instead, there's a gradual extension, each discovery pushing the boundary a little further, suggesting that the limits of structure might be broader than we once thought. But this doesn't mean that anything is possible. The underlying physics still matters. Gravity, the expansion of the universe, the distribution of matter in the early universe, all of these factors influence how large structures can become. So when a structure appears that seems unusually large, it's not just a curiosity, it's a clue, a hint about how these processes might be working on the larger scales, and comparing these giants helps provide context. It shows us that the HCB Great Wall is not an isolated anomaly, but part of a broader pattern of discovery. A pattern where structures of increasing size have been identified over time, each one prompting new questions, each one refining our understanding. There's also something gently humbling about placing these structures side by side, because even the largest among them are still part of something bigger. They exist within the cosmic web, they're connected directly or indirectly to other structures, and beyond them, the universe continues, extending further than we can observe. So the idea of largest becomes less about a final answer and more about our current horizon. The largest structure we know today is simply the largest we have been able to identify so far, and that horizon can shift. As new observations are made, as new methods are developed, as more of the universe is mapped, the list of these giants may grow. Or our understanding of them may change. And that's part of what makes this exploration feel so open-ended. There's no sense of reaching a final boundary, only a gradual expansion of what we know. As you let that settle in, the HCB Great Wall becomes part of a larger story. Not just a single discovery, but one step in an ongoing process of uncovering the structure of the universe. Numbers can take us a long way. They give us a sense of comparison, a way to describe something that can't be touched or seen directly. When we say that the HCB Great Wall may stretch across around 10 billion light-years, we're using numbers to point towards something vast, but there comes a point where numbers begin to lose their grip. Not because they are wrong, but because our minds aren't built to feel them. 1,000 feels large, 1,000,000 feels enormous, 1,000,000,000 begins to blur. And when we add light years to that, a unit already far beyond everyday experience, the scale becomes something we can understand intellectually, but not quite hold in our imagination. So instead of trying to picture the HCB Great Wall all at once, it helps to approach it gently, step by step. Let's begin with something more familiar, the Earth. If you could walk all the way around it at the equator, you would travel about 40,000 kilometers. That's a long journey, but it's something we can imagine. Planes cross that distance in hours. Satellites orbit above it. Now expand that. The distance from Earth to the Moon is about 384,000 kilometers. Already the Earth begins to feel smaller in comparison. The Moon is far enough away that it takes light about 1.3 seconds to travel between them, and then, further still. The distance from Earth to the Sun is about 150 million kilometers. Light takes about 8 minutes to make that journey. At this point the scale is stretching, but it's still connected to things we know. Now consider the solar system. From the Sun to the outer edge, where distant icy objects drift in slow orbits, the distance can extend to tens of billions of kilometers. Light takes hours to cross it, and yet, compared to the galaxy, this is still a very small region. The Milky Way stretches about 100,000 light-years across. Now we've shifted units entirely, light-years instead of kilometers. And even here, the scale is already beyond anything we experience directly. If light itself, moving as fast as it possibly can, takes 100,000 years to cross our galaxy, then the galaxy is already something vast beyond ordinary imagination. But the HCB Great Wall is not the size of a galaxy, not even close. It is not the size of a cluster of galaxies, or even a supercluster. It extends across billions of light-years, so if you tried to place it alongside the Milky Way, you wouldn't see a comparison at all. The Milky Way would vanish into insignificance, like a single grain of sand compared to a continent. Even entire galaxy clusters would begin to feel small. And this is where our usual ways of picturing size begin to fail, because we rely on comparison. We imagine something large by placing it next to something else. But when the difference becomes too great, the comparison breaks down. It's like trying to compare the size of a room to the size of a planet. At some point, the smaller object becomes too small to meaningfully relate to the larger one. So instead of trying to picture the HCB Great Wall as a single object, it can help to think of it as a region. A stretch of space where galaxies, clusters and events are more densely arranged across an enormous distance. Not a solid wall, not something you could see from the outside, but a vast alignment woven into the cosmic web. And even then, the scale remains difficult. So let's try a different approach. Imagine travelling at the speed of light. Not something we can do, of course, but something we can use as a reference. At that speed, you could circle the Earth more than 7 times in a single second. You could travel from Earth to the Moon in just over a second, from Earth to the Sun in about 8 minutes, to the outer edge of the solar system in a matter of hours, to the nearest star in just over 4 years, across the Milky Way in 100,000 years, and then across the HCB Great Wall. You would still be travelling for billions of years, longer than the time it took for complex life to evolve on Earth, longer than the age of many stars, longer than most of human history by a factor so large that it becomes almost meaningless to compare. And yet even this thought experiment only gives us a faint sense of the scale. Because while we imagine travelling in a straight line, the universe itself is expanding. The distances between galaxies are increasing over time, so as you travel, the structure you are crossing is slowly stretching. The journey becomes even longer. And this introduces another subtle idea. The HCB Great Wall is not something fixed in place. It exists within an evolving universe. Its components are moving, drifting, influenced by gravity and cosmic expansion. So the structure itself is not static. It is changing slowly over billions of years, and that makes it even harder to picture. Because we are not just trying to imagine something large, we are trying to imagine something large and dynamic, something that exists across both space and time. At this point, it might feel like the mind begins to let go a little. Not in frustration, but in acceptance. The scale is simply too great to fully visualize, and that's okay, because the goal is not to hold the entire structure in your mind at once. It's to gently appreciate that such scales exist, that the universe contains patterns that extend far beyond anything we can directly experience. There's something quietly calming about that. The idea that not everything needs to be fully grasped, that some things can remain vast, distant, and only partially understood, and still be meaningful. As you sit with this, you might notice how the idea of beyond imagination doesn't have to feel overwhelming. It can feel soft, like looking at a distant horizon that you know you will never reach but can still appreciate. The HCB Great Wall is like that horizon, not something to fully capture, but something to gently consider. A reminder of how far the universe extends and how much there is beyond our everyday sense of scale. Before anything in the distant universe can be observed, there is always a quiet delay. Not a delay caused by instruments or technology, but something built into the nature of light itself. Light does not arrive instantly. It travels steadily and patiently across space, carrying information from where it began to wherever it is received. And when the distances are small, that delay is barely noticeable. Light from the Moon takes just over a second to reach Earth. From the Sun, about 8 minutes. Even from the outer edges of the solar system, only a few hours. But as soon as we begin looking beyond our galaxy, that delay stretches into something much more significant. When we observe a galaxy 1 million light years away, we are seeing it as it was 1 million years ago. When we look at something 1 billion light years away, we are seeing it as it was 1 billion years ago. And when we consider something as vast as the HCB Great Wall, spanning billions of light years, this idea becomes even more layered. Because we are not just looking at one distant object. We are looking across a region so large that different parts of it are being observed at very different moments in time. This is one of those details that can quietly change how we think about what we're seeing. It might be tempting to imagine the HCB Great Wall as a single structure existing now, stretched across space in its current form, but that's not quite how observation works. Instead, each point within that structure is seen at a different stage in its history. One part might be observed as it was billions of years ago. Another part, slightly closer, might be seen a little more recently. Closer still, and the time difference continues to shrink. So what we're really seeing is a kind of layered snapshot. Not a single moment, but a collection of moments stitched together by the time it takes light to travel. It's a bit like looking at a long train where each carriage shows a different point in its journey. One carriage might be just leaving the station, another might be halfway along the track, another might be nearing its destination. All of them belong to the same train, but each one is at a different stage. In the same way, the HCB Great Wall, as we observe it, is not a single moment frozen in time. It's a sequence of moments spread across billions of years, presented to us all at once. And that adds a quiet layer of complexity. Because when we talk about the size of such a structure, we're also talking about how it appears across time. The distances we measure are based on how far the light has travelled. But the actual configuration of matter in that region may have evolved since that light began its journey. Galaxies may have moved, clusters may have merged, new stars may have formed while others faded. The structure we observe is real, but it is also historical. It reflects what that region of the universe looked like over a vast span of time, rather than at a single instant. There's something quite gentle about that idea. The universe is not presenting itself as it is now, but as it has been. Every observation is a message from the past, and the further away we look, the older that message becomes. In fact, when we observe the most distant objects, we are looking back to a time when the universe itself was much younger. Galaxies were still forming, stars were igniting for the first time, the overall structure of the cosmos was still taking shape. So when we map something like the HCB Great Wall, we're also mapping a piece of that history. We're seeing how matter was distributed across a vast region at different points in the universe's evolution. And this has an interesting implication, because it means that the structure we observe is not necessarily the same as the structure that exists now, if such a concept can even be clearly defined. The universe has continued to evolve since the light we see was emitted, so the HCB Great Wall, as we detect it, is both a structure and a record. A structure in space, a record in time. And that dual nature can make it a little more difficult to interpret, because when we see a pattern across billions of light years, we have to consider not only how matter is arranged, but also how that arrangement has changed over time. Are we seeing a structure that existed in a similar form across that entire span? Or are we seeing a sequence of regions that were at different stages of development, appearing connected because of how their light reaches us? These are the kinds of questions that scientists explore when studying large-scale structures, and they don't always have simple answers, but that uncertainty is part of what makes the exploration meaningful. It reminds us that observation is not just about distance, it's about time, and the two are inseparable. As you sit with this idea, you might notice how it gently shifts your sense of the present. Everything you see, even in your immediate surroundings, is slightly in the past, because light takes time to reach your eyes. The delay is so small that we don't notice it. But on cosmic scales, that delay becomes the defining feature of how we observe the universe. We are always looking back, always receiving signals that have travelled for immense periods of time, and in a quiet way that makes the universe feel less like a fixed place, and more like a story unfolding across time. A story we can only read by looking at its earlier chapters. The HCB Great Wall is one of those chapters. Not a final image, but a glimpse of how matter was arranged across a vast region billions of years ago. And as we continue to study it, we're not just learning about its size, we're learning about the history it represents. Sometimes the hardest question in science isn't what are we seeing, but something quieter. Are we seeing it correctly? Because when patterns begin to emerge from limited data, especially across vast distances, there's always a gentle possibility that what appears structured might be something else entirely. Not false, not mistaken in a careless sense, but shaped by the way we observe, measure, and interpret. This is where the idea of illusion enters the conversation. Not illusion, as in something imaginary, but as something that looks more defined or more connected than it truly is. And when it comes to something as large as the HCB Great Wall, this question becomes especially important. The universe is vast, but our data is not infinite. We're working with a limited number of observations gathered over time, using instruments with their own constraints. Gamma-ray bursts, for example, are powerful, but they are also rare. Each one adds a point to the map, but the map itself remains sparse. Now, imagine placing a handful of points across a large space. Even if those points are distributed randomly, there's always a chance that some of them will appear to line up. Not because they are connected, but because randomness can produce patterns that look meaningful. It's a bit like looking at the stars in the night sky. We see constellations, shapes, familiar outlines. But those patterns are not physically connected. These stars are at different distances, unrelated in space, yet from our perspective they form recognizable figures. The same principle can apply, in a more subtle way, to large-scale cosmic data. When astronomers first noticed the clustering of gamma-ray bursts associated with the HCB Great Wall, the immediate question was not, what is this structure, but could this be a coincidence? To explore that, they turned to statistics. They asked how likely it would be for such a clustering to appear by chance if the bursts were randomly distributed. They ran simulations, generating random distributions of points and comparing them to the observed data. If the observed pattern appeared frequently in these simulations, it would suggest that the clustering might not be significant. But if it appeared rarely, then it would strengthen the case that the pattern reflects something real. The results suggested that the clustering was unlikely to be purely random, but unlikely is not the same as impossible, and that leaves room for careful interpretation. There's also the matter of selection effects. Not all parts of the sky are observed equally. Some regions are monitored more closely, some bursts are easier to detect than others, and some distances are measured with greater precision. These factors can influence the distribution of observed events. A region that appears dense with gamma-ray bursts might partly reflect where we've been looking more often, or where our instruments are more sensitive. So astronomers have to account for these effects. They adjust their analyses, correct for observational biases, and test whether the pattern remains after those corrections. And even then, there's the question of definition. What exactly counts as a structure? If you have a series of clusters that are loosely connected, at what point do they become a single, unified structure rather than a collection of separate ones? This is not always a clear boundary. It depends on how you define connectivity, how you measure density, and how you interpret the relationships between points. In some cases, different methods can lead to slightly different conclusions. One approach might identify a large continuous structure. Another might see a series of smaller, overlapping regions. Neither is necessarily wrong. They are different ways of interpreting the same data, and this is where perception plays a role. Not in a subjective sense, but in the sense that the way we choose to analyze and visualize data can influence the patterns we see. We are, in a way, translating the universe into something we can understand, and that translation always involves choices. Choices about thresholds, definitions, and methods. This doesn't mean that structures like the HCB Great Wall are illusions, but it does mean that their exact nature, their size, their boundaries, and even their classification can depend on how we interpret the data. There's something quietly reassuring about this. The idea that science does not rush to certainty, that it allows space for questioning, for alternative interpretations, for the possibility that what we see today may be refined tomorrow. It's not a weakness, it's a strength, because it keeps us open to new information, to better measurements, to deeper understanding. As you reflect on this, you might notice how the concept of illusion becomes less about doubt and more about perspective. Not, is it real, but how real and in what way? The HCB Great Wall, as it currently stands, is a pattern supported by data, a pattern that appears significant, a pattern that suggests a large-scale structure. But it is also part of an ongoing investigation, a piece of a larger puzzle that is still being assembled, and that's part of what makes it so interesting. It sits at the edge of what we know. Not fully uncertain, not fully settled, but in a space where curiosity remains active, where questions are still being asked, where new observations can still shift the picture. And perhaps that's a gentle reminder that understanding does not have to be absolute to be meaningful. We can appreciate the pattern, explore its implications, and remain open to the possibility that our view may continue to evolve. There is always a boundary to what we can see, not a sharp edge marked in space, but a quiet limit shaped by light, time, and the way the universe unfolds. No matter how advanced our instruments become, no matter how carefully we observe, there are regions we cannot reach with our senses, places from which no information has had enough time to arrive. This boundary is often called the observable universe. It is not the entire universe, just the portion we can access through light and other signals. Beyond it, there may be more galaxies, more structures, perhaps even patterns larger than anything we've detected, but they remain out of reach, not because they are hidden, but because their light has not yet had time to travel to us. And this has a gentle but important implication. Everything we know about the largest structures in the universe, including something like the HCB Great Wall, comes from within this limited window. We're not seeing the whole picture, we are seeing a slice. Even within that slice there are further limits. Our observations depend on the tools we use, telescopes, detectors, satellites, each with their own capabilities and constraints. Some can detect visible light, others focus on radio waves, X-rays, or gamma rays. Each reveals a different aspect of the universe, but none captures everything. So the map we build is always incomplete, not incorrect but partial. There are regions where our data is sparse, areas where observations are less precise, distances where measurements become more uncertain. And when we try to identify structures across billions of light years, those gaps and uncertainties begin to matter. A structure might appear continuous because we lack the data to see where it breaks, or it might seem fragmented because we haven't yet observed all the connections. This doesn't mean the structures are illusory, it means our picture of them is still being filled in. There's also the matter of distance itself. Measuring how far away something is in the universe is not as straightforward as measuring length on Earth. It relies on interpreting light, on understanding how it has been stretched, shifted, or altered during its journey. These measurements are precise but not perfect. There are uncertainties, small ones, but when extended across billions of light years, even small uncertainties can influence how we interpret the arrangement of objects. Two events that appear to be at similar distances might actually be separated by a greater amount than we estimate, or vice versa. And when we're mapping patterns, these details can subtly shape the structures we perceive. Another quiet limitation comes from time itself. As we discussed earlier, when we look at distant objects, we are looking into the past. But this also means that different parts of the universe are observed at different stages of their evolution. So when we map a large structure, we are combining observations from different times. This can create patterns that reflect both spatial arrangement and temporal sequence. And separating those two is not always simple. It requires careful modelling, an understanding of how structures grow and evolve, and a recognition that what we see is not a single snapshot but a layered history. There's also something more fundamental. We cannot step outside the universe to observe it as a whole. All our observations are made from within. This might seem obvious, but it has profound implications. It means that our perspective is always centered on our own location, even if we try to correct for that mathematically. We see the universe from here, from this point, with light arriving from all directions. And while the cosmological principle suggests that this view is not special, that any point in the universe would see something similar, we still cannot directly confirm that by moving to another location. We rely on consistency, on the idea that the laws of physics are the same everywhere, and that observations from our position are representative of the larger whole. And so far that assumption has worked well, but it remains an assumption, a very successful one, but still something we test and refine as we gather more data. When we consider something like the HCB Great Wall within these limits, it takes on a slightly different tone. It is not just a structure we have identified. It is a structure identified within the boundaries of what we can observe, using the data we currently have, interpreted through the models we use to understand the universe. And that doesn't make it less meaningful. If anything, it makes it more interesting, because it shows us how much we can infer, even with incomplete information, how patterns can emerge from limited data, how careful observation and analysis can reveal structures that are far beyond direct perception. There's something quietly reassuring about that. The idea that we don't need to see everything to understand something, that knowledge can grow gradually through observation, interpretation, and refinement, and that even within limits there is room for discovery. As you sit with this, you might notice how the concept of not knowing everything doesn't have to feel uncomfortable. It can feel open, like a horizon that continues to extend, inviting exploration without demanding immediate answers. The universe is vast and our window into it is limited, but within that window there is still so much to see, so much to map, so much to understand, and structures like the HCB Great Wall are part of that ongoing exploration. They are not final answers, they are pieces of a larger picture, one that continues to evolve as we look a little further, measure a little more carefully, and ask questions that reach just beyond what we currently know. Picture this instead of trying to measure it, not with numbers, not with maps, but by imagining a journey. You don't need to rush into it, just let the idea unfold slowly, the way the universe itself seems to prefer. Suppose somehow you had a way to travel across the HCB Great Wall, not as a beam of light, not instantly, but as an observer, moving steadily, able to notice what surrounds you as you go. At first, nothing would feel unusual. You wouldn't see a wall. There would be no boundary, no sudden edge where one region begins and another ends. You would simply be in space, surrounded by darkness, scattered with distant galaxies, each one a faint glow, far away and quiet. This is one of the first gentle surprises. Even inside one of the largest structures in the universe, most of what you would encounter is still empty space. Vast stretches where nothing much seems to be happening. You might travel for long periods without passing anything at all. No stars nearby, no galaxies close enough to stand out clearly, just the distant background of a light spread thin across the sky. And then, gradually, something would change. Not dramatically, just a subtle increase in presence. A few more galaxies appearing in certain directions, clusters becoming slightly more frequent. Regions where matter is just a bit more concentrated than average. This is how the structure reveals itself, not as something solid, but as a tendency. A region where the universe feels a little more populated, a little more connected compared to the emptier voids beyond. If you continued travelling, you might pass through a galaxy cluster. From a distance, it would look like a dense gathering of light. Dozens or hundreds of galaxies held together by gravity, each one moving slowly within the cluster's influence. If you could drift through it, you wouldn't feel anything in the usual sense. The distances between stars, even within galaxies, are so large that you could pass through without encountering anything directly. But visually it would be striking. Galaxies filling your field of view, glowing softly, each one a vast system in its own right. Then, as you move beyond the cluster, the density would drop again. back into quieter regions, then perhaps into another filament, another stretch of the cosmic web, where galaxies line up along a faint thread, connecting distant clusters, and this pattern would repeat. Density, then emptiness, clusters, then voids, all part of the same larger structure but never forming a solid, continuous object. Now consider the time it would take. Even if you were travelling at the speed of light, the journey across something like the HCB Great Wall would take billions of years, which means that by the time you reach the other side, everything around you would have changed. The galaxies you passed at the beginning of your journey would have evolved. Some might have merged. New stars would have formed. Others would have faded. The structure itself would not remain exactly the same. So this journey is not just through space, it is through time. Every step forward brings you into a different era of the universe's history. And this creates a quiet paradox. You are travelling across a structure that you can never experience as a whole, because the time it takes to cross it is so long that the structure changes as you move through it. You can observe parts of it, pass through regions, notice patterns, but the entire structure as a single entity remains something you can only understand indirectly, through maps, through data, through careful observation. There's something gently humbling about that. The idea that even if you could travel freely across the universe, there are scales at which direct experience is no longer enough. Understanding has to come from a different kind of perspective. Now, imagine slowing that journey down, not in speed but in focus. Instead of thinking about the entire distance, you begin to notice the details along the way. A galaxy here, a cluster there, each one with its own structure, its own history, its own quiet complexity. Because even within something as vast as the HCB Great Wall, the real richness lies in these smaller scales. The stars forming within galaxies, the interactions between galaxies, the slow movement of matter under gravity's influence. The larger structure is built from these smaller pieces, and experiencing it, even in imagination, becomes less about crossing the entire distance and more about noticing how those pieces fit together. It's a bit like walking through a forest. You might know that the forest stretches for miles, but as you walk, your experience is shaped by the trees immediately around you, the patterns of light and shadow, the gradual changes in density. The full extent of the forest exists, but your journey is always local, always focused on what is near, and the same would be true here. Even within one of the largest structures in the universe, your experience would be shaped by what surrounds you in each moment. The vastness would be there, but it would not press in on you all at once. It would unfold gradually, quietly. And perhaps that's what makes this thought experiment feel less overwhelming and more calming. The scale remains immense, but your experience of it remains manageable. You don't need to hold the entire structure in your mind. You can simply move through it, one region at a time, one cluster, one filament, one quiet stretch of space after another. And as you continue, you might notice something else. The idea of distance begins to soften, not because it becomes smaller, but because it becomes less central. The journey is not about reaching the other side, it's about the movement itself, the gradual unfolding of space and time, the quiet observation of a universe that is vast but not chaotic, structured but not rigid, and always evolving. Long before anything like the HCB Great Wall could exist, the universe was much simpler. Not empty, not featureless, but far more uniform than it is today. In its earliest moments, matter was spread out almost evenly, with only the slightest differences from one region to another. Tiny fluctuations, so small they might seem insignificant, were all that distinguished one part of space from the next. And yet, those tiny differences were enough. Because of gravity. Gravity is a quiet force. It doesn't act suddenly or dramatically on these scales. It doesn't pull things together in an instant. Instead, it works slowly, steadily, over immense periods of time, gently amplifying whatever differences already exist. If a region of space contains just a little more matter than its surroundings, gravity begins to pull additional matter toward it. Not quickly, not noticeably at first, but persistently. And as that region gathers more matter, its gravitational pull becomes slightly stronger, which allows it to attract even more. This is how structure begins, not from large dramatic events, but from small imbalances that grow over time. It's a bit like watching droplets form on a surface. At first, the surface is evenly covered, but small variations cause some areas to collect more water. Those areas grow, merging with nearby droplets, forming larger patterns. In the universe, the droplets are regions of matter, and the process unfolds over billions of years. As time passes, these regions become more defined. Matter flows along paths shaped by gravity, forming the filaments of the cosmic web. Galaxies begin to form within these filaments, drawn together into clusters, then into larger groupings, and slowly the universe develops structure. Not randomly, but guided by these initial conditions and the steady influence of gravity. Dark matter plays a crucial role in this process. Although it cannot be seen directly, it makes up most of the matter in the universe. It interacts through gravity, providing the scaffolding on which visible matter can gather. In the early universe, dark matter began to clump together first, forming the underlying framework of the cosmic web. Ordinary matter, the kind that forms stars and galaxies, followed this framework, falling into the gravitational wells created by dark matter. So when we look at large-scale structures, we're really seeing a combination of both. The visible galaxies trace out the structure, but the deeper pattern is shaped by something we cannot see. This adds another layer to the formation of gigantic structures. They are not just collections of visible matter. They are the result of an interplay between visible and invisible components, evolving together over time. As these structures grow, they begin to connect. Filaments stretch between clusters, clusters merge into larger systems, and the overall network becomes more pronounced. But this growth is not unlimited. The expansion of the universe introduces a counteracting effect. As space itself expands, it pulls regions apart, making it more difficult for gravity to bring distant areas together. On smaller scales, gravity dominates, allowing galaxies and clusters to form and remain bound. But on larger scales, expansion becomes more significant. This creates a balance. Gravity works to build structure. Expansion works to spread things out, and the structures we observe are the result of that balance over time. This is why there are expectations about how large structures can become. If gravity had unlimited influence, matter could continue to gather into ever larger formations, but because of expansion, there is a scale beyond which regions are no longer strongly connected. They drift apart rather than come together. So when something like the HCB Great Wall appears to extend across billions of light years, it invites a closer look at this balance. Is the structure truly connected in a gravitational sense? Or is it a pattern formed by regions that are part of the same general alignment, but not bound together in the way smaller structures are? This distinction is important, because a galaxy cluster is held together by gravity. Its components are bound, moving under their mutual attraction. But a structure on the scale of billions of light years is not bound in the same way. Its parts are too far apart for gravity to hold them together as a single unit. Instead, it is more like a pattern within the cosmic web, a region where matter has been distributed in a particular way during the universe's evolution. This doesn't make it less real. It simply means that its formation is different from that of smaller bound structures. It emerges from the overall process of structure formation, rather than from a single, cohesive gravitational system. And that process is influenced by the initial conditions of the universe. The tiny fluctuations present shortly after the Big Bang set the stage for everything that followed. The distribution of matter at that time determined where gravity would begin to gather material, where filaments would form, where voids would remain. Over billions of years, those initial patterns were amplified, stretched, and reshaped by gravity and expansion, leading to the complex structure we observe today. There's something quietly remarkable about that. The idea that something as vast as the HCB Great Wall may have its origins in tiny variations present at the very beginning of the universe. Small differences, growing slowly, shaping the distribution of matter across unimaginable distances. It's a reminder that scale in the universe is often deceptive. What appears enormous today can trace its origins back to something almost imperceptible, and the process that connects those two extremes is gradual, continuous, unfolding over time without any sudden leaps. As you sit with this, you might notice how the formation of these structures feels less like a dramatic event and more like a slow, steady evolution. There's no moment where a structure suddenly appears. It emerges, piece by piece, region by region, guided by forces that operate quietly but persistently. And perhaps that's part of what makes the universe feel so balanced. Even its largest structures are the result of simple processes, repeated over immense timescales, gravity pulling matter together, expansion stretching space apart, initial conditions setting the stage, and time allowing everything to unfold. Every so often in science, a discovery arrives that seems large enough to rewrite everything. But most of the time, that isn't what happens. More often, the changes are quieter, subtle adjustments rather than complete overhauls, a shift in perspective, a refinement of scale, a gentle expansion of what we thought we understood. And when it comes to something like the HCB Great Wall, the question is not so much, does this break physics? But something softer. What does this nudge us to reconsider? Because the fundamental laws that describe the universe, gravity, relativity, the behavior of matter and energy, remain remarkably stable. They have been tested across many scales, from the motion of planets to the bending of light around galaxies, and they continue to hold. The HCB Great Wall does not contradict these laws. It doesn't require a new kind of force or an entirely different framework. Instead, it sits within the existing picture, but near its edges. And that's where it becomes interesting. If a structure appears larger than expected, it doesn't immediately mean that the laws are wrong. It may simply mean that the conditions under which those laws operate allow for more variation than we previously assumed. In other words, the rules stay the same. But the range of outcomes might be broader. One of the areas this touches is our understanding of large-scale structure formation. Models of the universe, especially those based on the idea of cold dark matter and cosmic inflation, predict how matter should cluster over time. They describe the growth of filaments, clusters, and superclusters, and they suggest that beyond a certain scale, the universe should begin to look more uniform. Structures like the HCB Great Wall seem to approach, or perhaps stretch, that scale. So the question becomes whether these models already allow for such structures as rare but possible outcomes, or whether they need to be adjusted slightly to accommodate them more naturally. This is not a dramatic shift. It's more like tuning, refining parameters, improving simulations, incorporating new data. And this kind of refinement happens regularly in science. Each new observation adds a bit more detail, helping to sharpen the picture. There's also the role of statistics. Large-scale structure is not deterministic in the sense that every detail is fixed in advance. It is influenced by initial conditions, random fluctuations, and the complex interplay of forces over time. So even within a well-understood framework, there can be rare configurations that stand out. Structures that are larger, more extended, or more unusual than the average. The HCB Great Wall might be one of those. An example of how, within the same set of physical laws, the universe can produce a wide range of outcomes. There's something quietly reassuring about that. The idea that the universe is not rigid, that it allows for variation, that even within consistent rules there is room for complexity and surprise. Another area where this discovery has gentle implications is in how we define the scale of uniformity. As we discussed earlier, the cosmological principle suggests that the universe becomes uniform on sufficiently large scales. But sufficiently large is not a fixed number. It's something we estimate based on observations. If structures like the HCB Great Wall are confirmed to be as large as they appear, it may suggest that the scale at which uniformity emerges is larger than we thought. Again, not a contradiction, just a shift in where we place that boundary. And then there's the question of observation itself. Discoveries like this often highlight the importance of improving our data. More gamma-ray bursts, more galaxy surveys, more precise measurements of distance and distribution. As our observational capabilities grow, our picture of the universe becomes more detailed, and with that detail we can better understand whether structures like this are rare exceptions or part of a broader pattern. There's also a philosophical layer to all of this, not in the sense of abstract speculation, but in how we think about knowledge. We often look for clear answers. Is this correct or incorrect? Does this fit or does it not? But in practice, especially in fields like cosmology, the answers are often more gradual, more nuanced. A discovery doesn't immediately overturn what came before, it adds to it. It refines it. It invites us to look a little more closely, and that's exactly what the HCB Great Wall does. It doesn't demand a new set of laws, it invites a deeper understanding of how the existing laws play out on the larger scales. As you sit with this idea, you might notice how different it feels from the way we sometimes imagine scientific progress. There's no sudden upheaval, no dramatic shift where everything changes overnight. Instead, there's a steady accumulation of knowledge, a gradual adjustment of models, a quiet expansion of what we consider possible. And in that sense, the implications of the HCB Great Wall are not loud, they are subtle. They sit in the background, gently influencing how we think about scale, structure, and the distribution of matter in the universe. And perhaps that's fitting, because the universe itself, for all its vastness, often reveals its secrets in quiet ways, through patterns, through data, through observations that, at first glance, seem small, but over time add up to something much larger. Look at the universe from far enough away and it begins to resemble something unexpected. Not a perfectly smooth expanse, not a chaotic scatter, but something in between. A kind of patchwork, where regions of structure and regions of emptiness sit side by side, woven together in a pattern that feels both organised and irregular at the same time. This is one of the quieter truths about the cosmos. It is not purely orderly, it is not purely random, it is both. And that balance is what gives rise to everything we've been exploring, from galaxies to clusters to vast structures like the HCB Great Wall. If you return, just for a moment, to the idea of the cosmic web, you can begin to see this patchwork more clearly. There are filaments, long strands where matter gathers. There are nodes, dense regions where clusters of galaxies form. And there are voids, immense spaces where very little matter exists at all. Each of these elements plays a role. The filaments create connection, the nodes create density, the voids create contrast, and together they form a structure that is neither uniform nor completely disordered. It's a bit like looking at a quilt. From a distance you see the overall pattern, the arrangement of shapes and colours, but up close, each piece is slightly different, each patch with its own texture, its own variation. The universe, in a quiet way, behaves similarly. On large scales there is a pattern, on smaller scales there is variation, and the two coexist without contradiction. This idea becomes especially meaningful when we consider structures like the HCB Great Wall, because it is not an isolated feature, it is part of this patchwork, a region where the pattern becomes more pronounced, where the distribution of matter forms a larger, more extended alignment. But it still exists within the broader balance of the cosmic web. It doesn't replace the overall structure, it adds to it. There's something gently reassuring about that. The idea that even the largest structures are not separate from the whole, they're expressions of it, variations within a larger pattern. And this brings us to the idea of order within chaos. At first glance, the universe can seem chaotic. Galaxies scattered across space, stars forming and exploding, matter moving under the influence of gravity. It can feel unpredictable. But when you step back, patterns emerge. Not rigid patterns, not perfectly repeating ones, but consistent enough to reveal an underlying order. Gravity pulls matter into filaments. Expansion stretches space. Initial fluctuations grow into structures. These processes create a framework that shapes how matter is distributed. And within that framework, there is room for variation, for regions that are denser, for structures that are larger, for patterns that stand out. So the chaos is not without structure. It is guided, shaped, constrained by the laws of physics, and the order is not without variation. It allows for differences, for irregularities, for features that are not perfectly predictable. This balance is what makes the universe feel both complex and coherent. It is not a simple system, but it is not an arbitrary one either. And as you sit with this idea, you might notice how it softens the way we think about large structures. The HCB Great Wall is not something that disrupts the universe's order. It is something that arises from it, a larger than expected patch within the overall pattern, a region where the underlying processes have produced an extended alignment of matter. And perhaps that's what makes it feel less like an anomaly, and more like a natural extension of what we already understand. It doesn't need to be explained by entirely new principles. It can be seen as part of the same process that creates all structures, just expressed on a different scale. There's also something quietly comforting about the presence of voids in this patchwork, the empty regions, the spaces where very little happens, because they remind us that not everything needs to be filled. Not every part of the universe needs to be dense or complex. There is space for stillness, for openness. And those empty regions are just as important as the dense ones. They allow the structure to exist. They create the contrast that makes the patterns visible. Without them, the universe would look very different, less textured, less defined. So even emptiness has a role, and that too is part of the balance. As this idea settles, the universe begins to feel less like something overwhelming and more like something quietly intricate. A system where order and variation coexist, where patterns emerge without eliminating complexity, where even the larger structures are part of a broader interconnected whole. And in that sense, the HCB Great Wall is not just a large structure. It is a reflection of this patchwork nature, a reminder that the universe does not organize itself in simple, uniform ways, but in layered, evolving patterns that reveal themselves gradually. Somewhere within all of this, there is a quiet shift in perspective. Not a scientific one, not something that changes equations or models, but something more personal. Because when we spend time thinking about structures that stretch across billions of light years, it becomes difficult not to notice how small our own place seems by comparison. And yet, that smallness doesn't have to feel unsettling. It can feel grounding. Because while the HCB Great Wall and the cosmic web exist on scales far beyond anything we can experience directly, our role in this picture is not to match that scale. It is simply to observe it, to notice, to understand, even if only partially. There's something quietly remarkable about that. The idea that beings as small as we are, living on a planet orbiting a single star in one galaxy among billions, can still piece together a picture of the universe that extends across such enormous distances. We don't travel those distances. We don't see those structures directly. But through light, through data, through careful thought, we can begin to understand them. And that creates a kind of connection. Not a physical one, but an intellectual one. A sense that, even though we are small in size, we are not separate from the universe we are observing. We are part of it, made from the same matter, following the same physical laws, existing within the same vast structure. There's also something gently reassuring about the way scale works in this context. When we think about being small, it's often in comparison to something larger, but scale in the universe is layered. Yes, we are small compared to galaxies. Galaxies are small compared to clusters. Clusters are small compared to superclusters, and even those are small compared to structures like the HCB Great Wall. But at each level, things are complete in their own way. A single cell is small compared to a human, but it is still a complete system. A human is small compared to a planet, but still fully present within their own scale. So smallness does not mean insignificance. It simply means being part of a larger structure. And in that sense, we are exactly where we need to be. Observers within the universe, rather than outside of it. There's also the idea of perspective. We often imagine that understanding requires seeing everything at once, holding the entire picture in our minds. But as we've seen, even when studying the larger structures, understanding comes piece by piece, through observations, through patterns, through gradual refinement, and that means our way of knowing is not limited by our size. It's shaped by our approach. We don't need to be large to understand something large. We just need to be patient, careful, curious. There's a quiet beauty in that. The universe does not hide its structure behind scale. It reveals it through patterns that can be observed, measured, and interpreted, even if those patterns extend far beyond our direct experience. As you sit with this, you might notice how the idea of vastness begins to soften. It's no longer something that overwhelms, it becomes something that invites reflection, a reminder of how much there is beyond our immediate surroundings, but also of how much we are capable of understanding. And perhaps there's something comforting in knowing that, despite the immense scale of the universe, our experience of it remains grounded. We are here, in this moment, on this planet, within this galaxy. And even though the structures we've been discussing extend far beyond that, they do not diminish the significance of our own place. They simply add context, a broader backdrop against which our lives unfold. There's also a gentle sense of continuity. The atoms that make up our bodies were formed in stars. Those stars are part of galaxies. Those galaxies are part of clusters and superclusters, and those are part of the cosmic web. So in a very real way, we are connected to these structures, not just as observers, but as participants, small pieces of a much larger system. And that connection doesn't require us to fully comprehend the entire structure. It's enough to recognize that it exists, to appreciate that we are part of something vast, even if we only experience a tiny fraction of it. As this idea settles, it becomes less about scale and more about relationship. Not how big is the universe compared to us, but how do we fit within it? And the answer is not through size, but through presence, through awareness, through the quiet act of observing and understanding. As all of these ideas begin to settle, something quiet happens. Not out in the universe, not across billions of light years, but here, much closer. The scale gently shifts back. The vast structures we've been exploring don't disappear, but they soften, becoming part of a wider backdrop rather than the main focus. Because after travelling through concepts this large, there's a natural tendency for the mind to pause, to come back, not abruptly, not all at once, but gradually. You've just spent time considering something that stretches across a significant portion of the observable universe. Patterns of matter traced through fleeting bursts of energy. Structures so large that even light would need billions of years to cross them. And now, without needing to force anything, your attention can begin to return to something much smaller, something immediate, the space you're in right now. Maybe the room feels a little quieter than before, or perhaps it's the same as it was, but your awareness of it has changed just slightly. The sounds, if there are any, feel softer. The edges of things feel less sharp. It's interesting how that works. When you think about something vast, your sense of what is close can begin to shift. Not because anything around you has changed, but because your perspective has. The HCB Great Wall still exists far away, stretched across distances that are difficult to fully imagine. The cosmic web still connects galaxies in patterns that extend beyond what we can see directly. The universe continues to expand, quietly, steadily, without needing our attention to do so. And at the same time, you are here, in this moment, breathing, listening, existing within a scale that is entirely your own. There's no need to hold both of those perspectives at once. You can let the larger one drift gently into the background, like a distant horizon that remains present but no longer demands focus. And in doing so, something else becomes clearer. The contrast between scales doesn't diminish either one. It simply places them side by side, the vast and the immediate, the distant and the near, the billions of light years and the space around you right now. And both are real. Both are part of the same universe. There's something quietly reassuring in that. The idea that the same physical laws that shape structures like the HCB Great Wall also shape the world you experience directly. Gravity, light, time, matter, all of it operates consistently, whether across galaxies or within the space you're sitting in. It's not a separate system, it's one continuous whole. And within that whole, your experience is not insignificant, it's simply at a different scale. As this thought settles, you might notice you're breathing again. Not in a deliberate way, not something you need to control, just a gentle awareness of it. In, out, steady, unhurried. There's a rhythm to it that doesn't depend on anything else, not on the size of the universe, not on the structures we've been discussing, just a quiet, ongoing process, and perhaps that rhythm feels a little more noticeable now. After spending time with ideas that stretch across billions of years and light years, something as simple as a single breath can feel grounded, immediate, present. There's no need to think about distances anymore, no need to map structures or imagine scales. You can let those ideas rest. They don't need to be held actively. They can remain somewhere in the background, like something you've gently set down after carrying it for a while, and as your attention settles further, you might notice how the mind itself begins to slow, not stopping, not becoming empty, but moving with less urgency. Thoughts that were more active earlier might now feel softer, less defined, and that's perfectly fine. There's no need to hold on to any particular idea, no need to follow every thought to its conclusion. You can let them pass, the same way light passes across space, quietly, without effort. There's also something quietly comforting about the idea that, while the universe is vast, your experience of it doesn't need to match that scale. You don't need to understand everything. You don't need to visualize every distance. It's enough to know that these things exist, that the universe contains patterns and structures far beyond what we encounter in daily life, and that, in some small way, you've taken a moment to explore them. That's all. Nothing more is required. As you sit with that, the sense of scale can gently fade into something softer. Not gone, but less defined. The idea of billions of light years becomes more like a distant memory than an active thought, and in its place something simpler remains. The present moment, the quiet, the steady rhythm of your breathing. If you notice any tension, any lingering sense of effort from following along, you can let that ease as well. There's no need to hold on to anything, no need to keep track of where we've been. The journey has already unfolded, and now it's simply a matter of letting things settle. In a way, this mirrors something we touched on earlier, the idea that understanding often comes piece by piece, and that it doesn't need to be complete to be meaningful. You've moved through ideas about structure, scale, observation, time, and the limits of what we can know. And you don't need to hold all of that in your mind right now. It can rest. The universe continues on its own. The structures remain where they are. The patterns continue to evolve, and you can simply be here. There's something quietly grounding about returning to this scale, not because it is smaller, but because it is immediate. You don't need to imagine it. You don't need to measure it. It's already here. And as you continue to settle, you might notice how the sense of distance, both physical and mental, begins to soften even more. The far away becomes less distinct, the near becomes more present, and the difference between the two feels less important, because in this moment there is only what you are experiencing. The rest can wait. There's no rush to return to thinking about large structures or distant galaxies. They will still be there later. They are not going anywhere, and you don't need to follow them any further right now. Instead, you can let your attention rest, gently, without effort. If your eyes are open, they might feel a little heavier. If they're closed, perhaps there's a sense of stillness behind them. Either way, there's no need to change anything. Just let things be as they are. The universe in all its vastness continues quietly, and here, in your own small corner of it, everything is calm, everything is steady, everything is enough, and if sleep is beginning to come, you can let it. There's no need to hold on to the last words, no need to follow every thought. You can simply drift, softly, gently, at your own pace. And wherever you are, whatever time it is, this moment is yours. Quiet, unhurried, and perfectly placed within something vast, yet somehow still close enough to feel like home.